From dark matter to exoplanets, from the Big Bang to black holes, our universe is full of phenomena that challenge our understanding of physics. In this documentary, we will explore the most fascinating mysteries of the universe, explore current scientific theories and modern observations. Join us as we explore the most fascinating mysteries in the universe. The observable universe, which represents the part of the universe that we can see or find from Earth, extends approximately 13.8 billion light-years in all directions. In this vast space, there are billions of galaxies, each containing millions or even billions of stars and countless planets. The limit of this observable is the speed of light. Nothing beyond this distance is visible because the light from these objects has not reached us long enough since the beginning of the universe. What makes the observable universe so fascinating is that it is not only the stretched fabric of space, but also the rich tapestry of cosmic history. Light from distant galaxies gives us a glimpse into the universe's past, showing how celestial bodies have evolved over billions of years. When we look deeper into space, we are actually looking back, witnessing events that happened long before humanity existed. Instead, the entire universe includes everything, including regions beyond our reach. These regions may contain more galaxies, stars, and planets than we can see because of the brightness of these objects, or because they are so far away from us that their brightness changes in our view. The true size of the universe is still a subject of speculation and research, as we do not know whether it is finite or infinite in size. Additionally, we have a well-defined limit to the observable universe, and the entire universe is far beyond that limit, possibly infinite. This reality challenges our understanding of the cosmos, prompting scientists to explore theories about its orbit and structure, while grappling with the mysteries of dark matter and dark energy, which make up an important part of the universe's overall composition. Measuring the size of the observable universe depends on the principles of observation, light travel time, and cosmology. The basis of this measurement begins with understanding the speed of light, which is constant in a vacuum and takes 8 minutes to travel from the Sun to the Earth. When astronomers observe distant galaxies, they receive light that takes billions of years to reach us. This light effectively acts as a time capsule, allowing us to see these galaxies as they once were. To calculate the size of the observable universe, astronomers determine the distance to various celestial bodies using a variety of methods, such as parallelism, standard candles, such as supernova, and redshift. Parallax involves observing a nearby star from two different positions in Earth's orbit, which can cause it to be farther away than our own solar system. The standard candle relies on the predicted brightness of certain types of supernovae or variable stars, allowing astronomers to calculate the distance based on their obscurity. Redshift, on the other hand, measures the change in wavelength of light from distant galaxies as they move away from us, confirming that the universe is expanding and helping to estimate distance. When these distances are measured, the maximum observable distance is determined, which ends at the boundary of the observable universe. Given the expansion of the universe after the Big Bang, the light we see from the most distant places has traveled for billions of years. Hence, the outer reaches of the observable universe can be estimated to be approximately 13.8 billion light-years in each direction. These calculations are continually refined with advances in technology and improved tracking methods. Instruments like the Hubble Space Telescope and future missions like the James Webb Space Telescope will enhance our understanding of cosmic distances. As our ability to observe the universe grows, we realize its vastness, not only the distances we can measure, but also the regions we cannot reach. The most distant objects we see in the observable universe are primarily galaxies, some of which began shortly after the Big Bang. One notable example is a galaxy called GNZ11, located about 13.4 billion light-years from Earth. According to observations, this galaxy was formed about 600 million years after the creation of the universe. When observing GNZ 11 at this incredible distance, we are looking back at the earliest times in cosmic history, imagining the formation of galaxies after the universe began to cool and expand. Another amazing object is a galaxy called HD1, which is reported to be about 13.5 billion light-years away. This has led astronomers to believe that GNZ may have formed earlier than 11, allowing researchers to study the conditions common to the universe's infancy. The light observed from these galaxies provides key information about star formation processes and the evolution of space structures in the early universe. In addition to these galaxies, scientists are also identifying very distant quasars. Quasars are extremely luminous active galactic nuclei produced by supermassive black holes at the centers of galaxies. One of the most distant known quasars, designated J001, is located about 13 billion light-years away. Formed 700 million years after the Big Bang, it shows how galaxy formation happened in the early stages of the universe. These distant objects challenge our understanding of cosmic evolution because they reveal the conditions that existed when the universe was still young and disordered. They prompt astronomers to think more deeply about the fundamental laws governing galaxy formation and cosmic dynamics. Each discovery brings us closer to unlocking the mysteries of the universe, prompting exploration to observe more distant celestial bodies and better understand the time of evolution. Our understanding of the observable universe has changed dramatically since humanity first looked up at the night sky. In ancient times, the celestial bodies were often viewed through the lens of mythology and religion, with civilizations depicting the stars without understanding their true nature. The Renaissance marked an important turning point when astronomers such as Copernicus and Galileo challenged the geocentric model, where the Earth was not the center of the universe, but revolved around the Sun in a vast space filled with countless stars. As telescopes develop, so does our understanding of the structure and scale of the universe. The advent of the 18th and 19th centuries brought figures such as Edwin Hubble, whose observations showed that many galaxies are actually separate galaxies, dramatically expanding our understanding of the cosmos. Hubble's discoveries have led to the realization that our galaxy is not just one of many, but galaxies are moving away from us, supporting the idea of an expanding universe. This observation laid the foundation for the Big Bang theory, changing our understanding of the cosmic origins and evolution of the universe. In recent decades, the discovery of the cosmic microwave background radiation has allowed scientists to probe the early moments of the universe for the Big Bang model. Technological advances, including space telescopes and detection methods, have further enhanced our ability to observe distant galaxies, led to advances in measuring the universe's expansion rate, and understanding dark matter and dark energy. These components form a fundamental part of the structure of the universe, but their nature remains one of the greatest mysteries in modern cosmology. As our observational capabilities improve, so does our appreciation of the complexity of the universe. New missions like the James Webb Space Telescope are expected to further push the boundaries of our understanding by probing the early formation of galaxies, stars, and planetary systems. As we explore the observable universe, scientists and enthusiasts alike are invited to ponder the vastness, fascinating mysteries of space and our place in it. The cosmic microwave background, often referred to as the CMB, plays an important role in understanding the observable universe. This weak state after the Big Bang is the main evidence supporting the Big Bang theory, which describes the origin and evolution of the universe. Discovered in the mid-20th century, the CMB shows remnants of thermal radiation from a young, hot, and dense universe about 390,000 years after the Big Bang. The CMB is scattered across the sky and can be found in every direction, providing a snapshot of the universe in an important phase called recombination. At this point, protons and electrons combine to form neutral hydrogen atoms, which allow photons, or light particles, to travel freely. Before recombination, the universe was filled with opaque, light-emitting free electrons. CMB emission indicates that the universe is transparent, allowing light to pass through space. By analyzing small temperature variations and anisotropies in the CMB, scientists can gain valuable information about the structure, composition, and evolution of the universe. These changes represent density variations that eventually lead to the formation of galaxies and clusters. The CMB data also help determine key cosmological parameters, including the age of the universe and its contents, normal, dark, and dark energy. In addition, the CMB provides a framework for understanding the larger scale of the universe. Measurements from missions such as the Wilkinson Microwave Anisotropic Probe and the Planck satellite have allowed scientists to refine models of cosmic evolution, improving our understanding of fundamental questions about the geometry of the universe and its rate of expansion. As the cornerstone of modern cosmology, the cosmic microwave background remains a major research focus, opening new avenues to explore the mysteries of our universe and its origins. Several lines of evidence support the Big Bang Theory, which describes the origin and evolution of the universe. One of the most important pieces of evidence is the cosmic microwave background, or CMB. This radiation left over from the early universe is uniform in the background sky and serves as a snapshot of the Big Bang about 390,000 years after. The existence of the CMB is consistent with the predictions of the Big Bang model and suggests that the universe expanded from a hot, dense state where this radiation can now be detected. Another key piece of evidence comes from the observed changes in distant galaxies. Edwin Hubble's observation that galaxies are moving away from us, and the farther away they are, the faster they seem to shrink, supports the idea that the universe is expanding. This phenomenon, known as Hubble's law, suggests that the universe was once confined to a smaller point, consistent with the Big Bang theory. If the universe is expanding today, this suggests that it must have evolved from a hot, compressed state. Furthermore, the abundance of light elements provides strong support for the Big Bang theory. The theory predicts that the early universe created helium, deuterium, and other light elements through a process known as Big Bang nucleosynthesis. Observations of the current abundance of these elements in the universe are consistent with predictions that they formed in the hot, dense conditions that characterize the early universe. In addition, the large-scale structure of the universe also supports the Big Bang theory. The distribution of galaxies and galaxy clusters over cosmic distances shows patterns that can be explained by changes in the density of the larger universe as it cooled and expanded. Computer simulations based on the Big Bang successfully reproduce these structures, further strengthening the model's validity. Together, this evidence suggests that cosmic evolution is consistent, making the Big Bang theory the preferred explanation for the origin of the universe. In the first few seconds after the Big Bang, the universe underwent rapid and extreme changes in temperature, density, and energy. This period, known as Planck's epoch, lasted from 43 seconds to about 10 seconds. The universe was unimaginably hot, with temperatures exceeding temperatures never seen before, and it was filled with a dense mixture of elementary particles like quarks, electrons, and neutrinos, all in a state of chaos and equilibrium. The universe cooled significantly as it expanded. In the next few moments, within the first 100 seconds, the quarks began to combine, creating protons and neutrons in a process called baryogenesis. These protons and neutrons then went through a rapid process of formation called nucleosynthesis, which gave rise to heavy nuclei. Helium was formed as a primary product, along with other light elements such as deuterium and lithium. This process of synthesis laid the foundation for the elemental composition of the universe. Helium was formed as a primary product, along with other light elements such as deuterium and lithium. This process of synthesis laid the foundation for the elemental composition of the universe. About 390,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine and fuse into neutral hydrogen atoms, marking a moment known as recombination. This transition transformed the universe from opaque plasma to open space, allowing photons to travel freely. The emission of these photons is what we now call the cosmic microwave background radiation. The dynamics of this early universe were governed by fundamental forces. As it expanded, gravity began to exert its influence, leading to the formation of the large-scale structures we observe today. The seeds of galaxies were planted in the density fluctuations of the early universe, eventually leading to the rich complexity of cosmic structures that continued to evolve over billions of years. This early period after the Big Bang created the laws of physics and the fundamental particles that make up matter in the universe, laying the foundation for everything that followed. Cosmic inflation refers to the brief, exponential expansion of the universe that is believed to have occurred in the first fraction of a second after the Big Bang, from 10 to negative 32nd to negative 35th of a second. During this period, the universe expanded at an astonishing rate, expanding at least 100 trillion times. This incredibly rapid evolution helps explain several critical features of the universe we observe. One of the most powerful implications of cosmic inflation is its ability to account for the observed uniformity of the universe, often called isotropy. Looking anywhere in the sky, astronomers find the cosmic microwave background radiation with only small, consistent changes in temperature. Without inflation, it would be difficult to explain why distant and thus seemingly unrelated regions of the universe exhibit such uniform characteristics. Inflation suggests that these parts of the universe were once close together before rapid expansion pulled them apart, erasing the initial disorder and leading to the convergence we observe. Inflation also provides an explanation for the larger structure of the universe. In the first moments after the Big Bang, quantum fluctuations at the subatomic level were amplified. As the universe expanded, these changes extended to cosmic scales, serving as the first seeds for the formation of galaxies and other structures. Therefore, cosmic inflation not only unifies the unity of the universe, but also provides a basis for understanding the density fluctuations that eventually led to complex cosmic formations. Further, inflation predicts that the universe is not only flat, but has a large-scale structure influenced by the distribution of matter and energy. Observational evidence, including the cosmic microwave background and large-scale galaxy studies, supports the universe's geometric properties consistent with inflation. As our understanding of inflation continues to grow, it continues to provide fascinating insights into the nature of the universe and the mechanisms that govern its expansion and construction. The formation of the first elements in the early universe occurred through a process known as Big Bang nucleosynthesis. This process occurred in the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear reactions to occur. In the beginning, the universe was filled with high-energy plasma, consisting mainly of protons, neutrons, and electrons. As it expanded and cooled, conditions became favorable for these subatomic particles to combine and form simple nuclei. In the first moments after the Big Bang, protons and neutrons were formed from quarks, the fundamental particles from which protons and neutrons were formed. Soon these protons and neutrons began to fuse together through nuclear fusion. During the first few minutes, most of the protons were combined to form helium nuclei, specifically helium-4, which consists of 2 protons and 2 neutrons. In addition to helium, trace amounts of other light elements such as deuterium, lithium, and beryllium were also synthesized during this period through various fusion reactions. The equilibrium found at this stage of nucleosynthesis was very sensitive to the temperature and density of the universe. As the universe continued to expand and cool, fast nuclear reactions became too cool to continue, stopping the formation of new nuclei. About 5 minutes after the Big Bang, the universe had cooled enough that about 25% of its mass was helium, and the remaining 75% was hydrogen, with small amounts of deuterium and lithium. The basic elements formed during this critical period laid the foundation for the subsequent formation of stars and galaxies. Then, over billions of years, the stars burned, fusing hydrogen and helium into heavier elements through stellar nucleosynthesis. Hence, the matter in our universe evolved into the rich array of elements we observe today, which eventually contributed to the formation of the planets and the fundamental components of life. The study of Big Bang nucleosynthesis remains crucial to understanding the origin and significance of these early elements in the cosmic timeline. The cosmic web is the large-scale structure of the universe, resembling a network of interconnected filaments and bubbles formed by galaxies, galaxy clusters, and dark matter. This is a remarkable representation of cosmic architecture, where galaxies are not randomly distributed, but aligned in complex patterns. The Milky Way consists of dense regions called nodes or clusters, separated by large voids containing very few galaxies. The formation of the cosmic web began with quantum fluctuations in the early universe, shortly after the Big Bang during the inflationary period. These small density variations in the primordial plasma served as seeds for large-scale structures that would grow over billions of years. As the universe expanded and cooled, matter began to clump together under the influence of gravity. Regions that were slightly denser than their surroundings attracted more matter, leading to the formation of the first stars and galaxies. Over time, as gravity continues to pull matter together, these initial structures coalesce and grow, forming larger and more complex configurations. Gravitational interaction between visible matter and invisible dark matter has contributed to the development of large structures. Dark matter, which does not interact with electromagnetic forces, makes up a large part of the mass of the universe and plays an important role in the formation of the cosmic web. It affects the attraction and organization of simple matter into filaments and knots in the universe. As galaxies formed and evolved, they accumulated gas and dust, creating favorable conditions for star formation. Clusters of galaxies formed from the merger of smaller groups, and their gravitational pull further affected the surrounding structures. The complex network that characterizes the cosmic web is evidence of the dynamic processes of cosmic evolution. Current observational techniques, including large-scale galaxy surveys and simulations, are constantly improving our understanding of the cosmic web, revealing its complexity and the fundamental physics that govern the growth and spread of galaxies in the universe. The dark matter proposal arose from several key observations in astrophysics that revealed a discrepancy between the matter seen in galaxies and the gravitational effects observed in these systems. One of the earliest indications came from the study of galaxy rotation curves. Astronomers expected that the speed at which the stars rotate around the galactic center would decrease with distance, just as the planets behave in our solar system. However, observations have shown that stars outside galaxies are moving at high speeds, indicating that they have more mass than visible stars and gas. This discrepancy suggests that there is an invisible mass, often called dark matter, that exerts a gravitational influence on the stars. Another important piece of evidence came from the study of galaxy clusters. Observations have shown that the mass of galaxy clusters, determined by various methods, and the motions of individual galaxies within them, is much greater than the mass that can be calculated from visible matter alone. The gravitational pull of the clusters showed an abundance of luminous matter, further supporting the dark matter hypothesis. The existence of dark matter has been further supported by observations of the gravitational lensing effect, where light from distant galaxies is bent around large clusters of galaxies. The observed lensing volume often exceeds the mass associated with the visible components, representing much of the invisible matter. In addition, measurements of the cosmic microwave background radiation provided further evidence for dark matter. The patterns of temperature changes in the CMB serve as a snapshot of the early stages of the universe and can be interpreted to reveal information about the general contents of the universe. The data showed that dark matter makes up a large fraction of the total mass energy content of the universe. These compelling observations have led scientists to conclude that they cannot explain the gravitational phenomena observed in galaxies and galaxy clusters. Dark matter is an important component of the universe, influencing the structure and dynamics of cosmic systems, but its exact nature remains one of the most important mysteries in modern astrophysics. Gravitational lensing and galactic rotation curves are two important observational phenomena that provide compelling evidence for the existence of dark matter. Gravitational lensing occurs when light from a distant object, such as a galaxy, passes near a larger object, such as a galaxy cluster. The gravitational field of a large object twists the space around it, causing light to bend. How does a lens treat light? This effect can produce multiple images of the same distant object, distort the appearance of background galaxies, or create rings known as Einstein rings. When astronomers analyze the amount of lensing, they find that the bending of the observed light often exceeds what can be calculated based on the apparent mass of the galaxy cluster. The discrepancy suggests the presence of extra invisible mass, dark matter, that contributes to gravitational pull and affects how light bends. Galactic rotation curves provide conclusive evidence for dark matter by studying the motion of stars in galaxies. When scientists measure the rotation speed of stars at different distances from the galactic center, they expect to see a line that decreases with distance, similar to the behavior of the planets in the solar system. However, observations show that stars far from the center of galaxies orbit at high speeds that do not slow down as expected. This flat rotation curve suggests that the galaxy has more mass than observed because the visible matter, stars, gas, and dust, is insufficient to explain the high rotation speed. Dark matter, which forms extended halos around galaxies, accounts for the gravitational force required to maintain these velocities at large radii. Together, these two lines of evidence provide a consistent picture of a universe dominated by dark matter. Gravitational lensing suggests that galaxy clusters contain invisible mass, while galactic rotation curves show that the galaxies themselves are covered by extensive dark matter. Both phenomena challenge not only the existence of dark matter, but also our understanding of the universe, leading to explorations of its properties and interactions. The leading candidates for dark particles include several theoretical possibilities, the most prominent of which are weakly interacting particles, or WIMPs. WIMPs are hypothesized particles that have masses in the range of a few giga-electron volts to a few hundred giga-electron volts. They interact with the weak nuclear force and gravity, making them difficult to detect, but are plausible as components of dark matter. Theoretical frameworks such as supersymmetry, which extend the standard model of particle physics, predict the existence of WIMPs, particularly light supersymmetric particles, which may serve as candidates for dark matter. Another candidate is axions, hypothetical elementary particles proposed in theory to solve the strong CP problem in quantum chromodynamics. Axons have very small masses and are expected to interact very weakly with ordinary matter. Their unique properties suggest that they may make up a large portion of dark matter, and researchers are looking for them through a variety of detection methods, including looking for axion electric fields in strong magnetic fields. Sterile neutrinos are also considered potential candidates for dark matter. Unlike normal neutrinos, sterile neutrinos are not affected by the weak force, but are affected by the gravitational force. They may have been produced in the early universe and may provide a mechanism to explain observed discrepancies in galaxy formation and structure. Their properties allow for both warm and cold dark matter scenarios to be considered, making them versatile candidates. Finally, black holes are another interesting possibility. These black holes may be due to changes in density, rather than the collapse of stars in the oldest universe. If they exist with masses ranging from small asteroids to several solar masses, they could contribute to the dark matter of the universe. The search for identification and characterization of these candidates continues, with experiments and observations dedicated to uncovering the nature of dark matter. Each of these candidates provides intriguing insights into the composition of our universe, inviting extensive research to understand their existence and interactions. Dark energy is the mysterious force driving the rapid expansion of the universe. It is believed to make up about 70% of the total energy density of the universe. Unlike dark matter, which is attracted by gravity, dark energy acts against gravity, causing galaxies to grow apart. This leads to the complex understanding that gravity must be slowing down the expansion of the universe. Dark energy accelerates it. The discovery of dark energy was observed in the late 20th century. In the mid-1990s, two independent teams of astronomers attempted to measure the expansion rate of the universe using supernova Ia as a standard candle. They would find that the expansion is slowing down due to gravitational effects. However, surprisingly, the light from these distant supernovae was darker than expected. This unexpected dimming suggests that supernovae are farther away if their expansion is slower. Instead, they assumed that the expansion of the universe was accelerating. These discoveries laid the groundwork, and something unseen drove this acceleration, leading to the formation of the concept of dark energy. The equation of state for dark energy relates its density to pressure, suggesting that it is a negative pressure that opposes the negative force of gravity on cosmic scales. Although various theories have been proposed to explain dark energy, including changes to the cosmological constant, quintessence, and general relativity, no definitive explanation has been given. Recent observations and studies, including measurements of the cosmic microwave background radiation and galaxy clusters, have confirmed the existence of dark energy and its influence on the evolution of the universe. The study of dark energy remains one of the most important challenges in modern cosmology, as understanding its nature can provide insight into the ultimate fate of the universe and the fundamental laws governing its expansion. Dark energy plays an important role in the dynamics of the universe's expansion. This mysterious force, revealed through observations of distant supernovae, accounts for about 70% of the total energy content of the universe. As gravity works to pull matter together, dark energy exerts an opposing pressure, pulling galaxies apart and accelerating their expansion. The concept of dark energy complicates our understanding of physics because it is different from any known form of matter or energy. The fabric of space itself is stretched by this enigmatic energy, as galaxies that once moved at a steady pace grow apart from each other. As the universe ages, this expansion is expected to accelerate even further, leading to a scenario where distant galaxies are hidden behind the expanding cosmic horizon, out of reach. One of the fascinating aspects of dark energy is that although it is uniform and smooth on large scales, how it originates or what its true nature is not completely understood. Some theories may be related to free space energy, while others speculate that it may be a property of gravity on cosmic scales. This interplay between dark energy and the expanding universe raises profound questions about the ultimate fate of what we know. As scientists continue to explore the mysteries of dark energy through a variety of tools, including sophisticated telescopes and space probes, understanding this force brings us closer to unlocking the mysteries of the universe. With each discovery, they improve our understanding of the cosmos and our place in it, while much of the universe remains an enigma. Exploring the edge of the universe through the lens of various religious perspectives provides fascinating insight into humanity's diverse belief systems and their interpretations of the cosmos. While the concept of the physical edge of the universe is a modern scientific curiosity, many religions have their own metaphysical or symbolic ideas about the boundaries and nature of existence. In Christianity, the universe is often viewed as the creation of an all-powerful God. Although the Bible does not explicitly discuss the physical structure or boundaries of the universe, it does imply the finitude of creation, which is controlled and sustained by divine power. Passages such as, "In the beginning God created the heavens and the earth," Genesis 1:1, suggest that the universe came into existence for a purpose and with an inherent order. The concept of heaven is often interpreted spiritually rather than physically, emphasizing a metaphysical edge where God's dominion reigns beyond the physical cosmos, representing a finite, infinite boundary beyond human comprehension. In Hinduism, the universe is cyclically created, preserved, and destroyed through the mechanisms of Brahma, Vishnu, and Shiva. The cosmos is seen as a manifestation of Vishnu, sustained by the complex and eternal dance of Shiva. In Hindu philosophy, the physical universe is often viewed as one of many possible realms in an infinite cosmic ocean, reflecting a more fluid and boundless concept of the universe. Rather than a fixed edge, the boundaries of the cosmos in Hindu thought are rather transitions between states of consciousness and existence, layers of reality perceived through the lens of spiritual awakening and understanding. Buddhism, which focuses on the inner realms of consciousness and enlightenment, often treats the boundaries of the universe in more abstract terms. The physical dimensions of the cosmos are less significant compared to the mental and spiritual landscapes that are explored through meditation and mindfulness. The idea of the edge is symbolic, representing the limits of individual perception and the potential for overcoming suffering and ignorance to reach a state of nirvana, the ultimate reality beyond physical limitations. Islam, like Christianity, views the universe as the creation of an omnipotent God, Allah. The Quran states that the heavens and earth were created by Allah, and speaks of the vastness and careful orderliness of the cosmos. Although it does not specify a physical boundary, it emphasizes that everything in the universe is subject to the will of God. Allah's knowledge and power extend beyond any physical boundaries, suggesting that the true edge of the universe is where human understanding ends and divine wisdom begins. These religious interpretations offer rich and varied perspectives on the concept of the edge of the universe, integrating physical, metaphysical, and spiritual dimensions to provide a holistic understanding beyond mere physical boundaries. They remind us that the quest to understand the cosmos is as much a journey of inner discovery as it is an exploration of outer space. Christianity's view of the concept of the edge of the universe is closely intertwined with its theological worldview, which emphasizes creation, divine order, and the omnipresence of an omnipotent God. While the Bible does not discuss the physical boundaries of the world in the modern scientific sense, it does provide a framework by which believers can see the world and its boundaries. Christian doctrine asserts that God is the creator of all things, and this belief can be found in scriptures such as Genesis 1:9, 7:4, 7:4 von den, which states that in the beginning God created the heavens and the earth. This main verse states that the world is a small creation created by God's will, but it does not refer to physical dimensions or dimensions. On the other hand, the Bible often uses poetic language and metaphors to describe the whole world and affirms the sovereignty and ultimate power of God. For example, Psalm 19:1 states, "The heavens show the glory of God. The firmament is the work of His hands." It illustrates a view of the universe as evidence of divine mastery and majesty. The concept of the edge of the universe in Christian thought is symbolic rather than literal. It represents the limit of human understanding and the point at which earthly knowledge gives way to the mystery of divine wisdom. Verses such as Isaiah 40:22, which speaks of God sitting on a throne above the circle of the earth, and Job 26:7, which describes how God stretches the northern sky over empty space and suspends the earth above nothing, emphasize the immeasurable and awe-inspiring nature of God's creation. These passages emphasize that although the universe has physical boundaries, to comprehend them completely is beyond the power of man, and only God has complete knowledge of the cosmos. Furthermore, Christianity affirms an ultimate reality that transcends the physical universe. The promise of eternal life and the existence of a heavenly kingdom, described in texts such as Revelation 21, which speaks of a new heaven and a new earth, suggests an existence beyond the finite boundaries of the known universe. This realm is portrayed as the place where God's presence is fully realized and where believers are united with the divine. Christianity views the edge of the universe not only as a physical boundary, but also as a metaphor for the limits of human understanding and the immensity of God's creation. The focus is not so much on where the universe ends, but on glorifying God as the creator and sustainer of all things, both visible and invisible, finite and infinite. Hinduism offers a rich and complex view of the universe and its boundaries, combining physical cosmology with deep metaphysical concepts. In contrast to the linear and limited interpretations found in Western thought, Hinduism views the world as an endless cycle of creation, preservation, and destruction. Hindu philosophy is based on the principles of time, the constant creation and decay of the universe, and yoga. These life cycles are governed by three gods: Brahma, the creator, Vishnu, the preserver, and Shiva, the destroyer. Brahma is believed to have created the universe over billions of years, Brahma's day, followed by a long period of decay, or Brahma's night. This cycle repeats itself ad infinitum, emphasizing the temporal and ever-changing nature of the world. Ancient Hindu texts, such as the Vedas and Puranas, describe the universe as consisting of multiple realms, or lokas, each with its own qualities and inhabitants. These realms are often represented as concentric spheres, or ascending planes that extend both beneath and above our visible world. These lokas extend from the earthly plane, Bhuloka, to the higher spiritual realms, Swagaloka and Vaikuntha, where divine beings and enlightened souls reside. Interestingly, Hindu scriptures often mention that the universe is like a cosmic ocean, boundless and infinite, reflecting the Hindu concept of the universe as Ananta, meaning infinity. In the Bhagavata Purana, for example, the universe is described as a huge lotus flower floating in the causal ocean, and countless such universes emerged from the clutches of Lord Vishnu during his yogic sleep. These images convey a universe without rigid boundaries, which is part of a larger, infinite space teeming with countless worlds and dimensions, each of which undergoes cyclical processes of birth, life, and dissolution. Furthermore, Hindu philosophy often emphasizes the unity of the Atman, the individual soul, with Brahman, the ultimate reality or world soul. This view inherently blurs the boundaries between microcosm and macrocosm, suggesting that the universe and its boundaries are not merely external, but are inextricably linked to the spiritual path and consciousness of human beings. Hinduism sees the universe as an infinite cyclic manifestation of divine principles, whose boundaries are metaphysical rather than physical. The eternal cycles of creation and destruction, the multiplicity of realms, and the ultimate unity of all things in the divine essence of Brahman are centered. This perspective fosters a holistic understanding of the cosmos that transcends physical limits and embraces the spiritual dimensions of existence. Islam provides a rich and layered view of realms beyond our observable universe, deeply rooted in its theological, philosophical, and metaphysical teachings. The Quran, the holy book of Islam, along with the hadiths, sayings, and actions of the Prophet Muhammad, offers insight into these dimensions, emphasizing both the greatness of God's creation and the existence of realms beyond human perception. One of Islam's fundamental concepts regarding the cosmos is the belief in the existence of multiple heavens, or samawat. In the Quran, the 7 heavens are mentioned in several verses, such as Surah Al-Mulk 67. 3. He made the 7 heavens a layer. You see no contradictions in the structure of goodness. These heavens are considered a vast, multi-leveled space beyond our earthly experience. Each has its own unique characteristics, and perhaps his people. Although the exact nature of these 7 heavens is not scientifically described, they are believed to be part of God's creations, reflecting the complexity and vastness of the universe. Also understand the social concepts of countries beyond our physical world. The most important work is the concept of Akhira, a hell according to which souls pass to another level of life after physical death. Some of them are Jannat, Paradise, and Jahannam, which are explained in the Quran and Hadiths. These realms are shown as rewards or punishments depending on one's actions in the world beyond our conscious world. Paradise is depicted as a place of eternal bliss and beauty, with descriptions of gardens, rivers, and palatial dwellings, as found in Surah Al-Baqarah 225, and announcing to those who believe and perform righteous deeds that they will have gardens in paradise, rivers flow beneath it. In contrast, hell is described as a place of severe suffering and torment. In addition, Islam includes the concept of al-ghaib, the unseen world, which includes not only paradise and hell, but also other spiritual beings and dimensions beyond human senses. They include angels, jinn, supernatural beings created from smokeless fire, and other elements that interact with the physical world but exist mainly in realms that lie beyond sense perception. The Quran often encourages belief in al-ghaib as an expression of faith in the unseen aspects of God's creation. Islam enriches our understanding of the universe by presenting numerous realms beyond the physical world we perceive. These realms, which include the 7 heavens, the future, and the realm of the unseen, serve to illustrate the vastness and complexity of God's creation. Differing from the empirical approach of modern cosmology, these beliefs emphasize a broader framework in which the physical universe is only one aspect of a much larger, multifaceted reality governed by a divine agency. Mystical and esoteric traditions of various cultures and spiritual systems often suggest the existence of higher planes of reality that are beyond our normal sensory experience. These planes are presented as realms of higher spiritual or metaphysical complexity, each with its own unique characteristics and laws. These teachings suggest that higher levels are accessible through inner transformation, spiritual practices, and heightened states of consciousness. Western esoteric traditions, such as Theosophy, and the writings of mystics, such as Emanuel Swedenborg, view the universe as multi-layered, consisting of multiple planes of existence beyond the physical. Theosophy, in particular, postulates a series of planes: physical, astral, mental, and higher spiritual, each corresponding to different forms of existence and consciousness. According to these teachings, the physical world is the most dense and material, while the higher planes are more subtle and ethereal. For example, the astral plane is believed to be the realm of emotions and desires, where one's thoughts and feelings have a tangible impact. The mental plane is associated with intellectual and rational thinking, and beyond it are the various spiritual planes where union with the divine becomes more pronounced. The Hindu and Buddhist esoteric traditions have detailed descriptions of higher realms, often called lokas in Hinduism or bhumi in Buddhism. Hinduism describes a cosmology with multi-layered worlds, including Earth, Bhuloka, the intermediate worlds, Bhuvarloka, and the higher celestial realms, Swagaloka. In these higher planes dwell gods, sages, and advanced spiritual beings. In Buddhism, the concept of the Pavakakra, or Wheel of Life, depicts different realms of existence, each representing different states of consciousness and moral development, ranging from the infernal realms to the celestial planes inhabited by deities and enlightened beings. Sufi works in the Islamic tradition explore the concept of multiple layers of reality. Sufi teachings speak of the soul's progression through various stages, stations, positions, and states, ahwalas, to reach the final connection with God or Godhead. The Latae Fasita, or 6 organs or centers, can be thought of as the intermediate point of consciousness that governs this journey. These centers reflect different aspects of spiritual growth and vision, and lead the seeker from the inner layers to higher reality. Magicians often emphasize that these higher levels represent not only external realms, but also states that one can experience within oneself. Practices such as meditation, prayer, rituals, and the cultivation of virtues are seen as means of purifying the mind and soul, allowing one to ascend through these planes. For many, these higher realms represent stages of enlightenment, in which the soul realizes its true nature and oneness with the greater cosmos, or divine essence. Mystical and esoteric beliefs suggest the existence of higher planes of reality as realms of great spiritual significance, each with its own unique attributes. These planes are accessed through spiritual practices and inner transformation, leading the seeker to deeper understanding, enlightenment, and union with the divine. These traditions offer a multidimensional view of existence in which the physical world is only one of many layers of a deeply interconnected and dynamic universe. Philosophical investigations into the nature of the universe cover a wide range of issues, delving into both the physical properties and the deeper metaphysical implications of existence. These questions seek not only to understand the structure and origin of the cosmos, but also to get to the essential meaning and purpose of the universe and our place in it. One of the central philosophical questions is the nature of reality itself. Philosophers have long debated whether the universe is material, consisting of physical matter and energy, or whether it has a dualistic nature, consisting of both material and immaterial components, such as mind or spirit. This inquiry moves into discussions about the nature of consciousness and whether it is a consequence of physical processes or indicative of a deeper immaterial reality. Another key question is the origin of the universe. What happened before the Great Collapse? Classical theories of physics contradict theories that existed before the Big Bang, since time and space as we know them arose from that event. Theoretically, this leads to the question of whether the world has a first cause, which often leads to interpretations of God as a universal argument for the existence of God. However, some theories suggest the existence of a self-created or eternal universe, which challenges our understanding of origins and time. The question of why the world exists is another profound aspect of philosophical inquiry. According to the famous philosopher and mathematician Gottfried Wilhelm Leibniz, why is there nothing? This issue concerns metaphysical ideas about life itself and the question of whether life in the universe can be explained by chance, randomness, or design. Philosophy also attempts to understand the basic laws that govern the universe. Do these laws exist in the universe, or are they determined by some external or other factor? The fine-tuning of the universe, where physical constants appear unusually precise for the development of life, raises additional questions about whether this is the result of chance, necessity, or some form of deliberate design, echoing debates in cosmology and theology about the anthropic principle. The multiverse theory adds another level of complexity by suggesting that our universe may be just one of an infinite number of universes, each with its own laws of physics and constants. It raises philosophical questions about existence and reality, such as whether all conceivable possibilities exist somewhere in the multiverse, and what follows with respect to causality and identity. Finally, the nature of time and space remains a rich field of philosophical inquiry. Is time a linear progression, an illusion, or a cyclical process? Are space and time fundamental aspects of reality, or are they emergent properties dependent on more fundamental principles? These questions affect the work of famous physicists and philosophers alike, reflecting ongoing debates about the very fabric of reality. Philosophical questions about the nature of the universe cover a wide range of fundamental issues, including the nature of reality, the origin and purpose of the cosmos, the underlying principles governing existence, and the structure and nature of time and space. These investigations seek not only to solve scientific riddles, but also to better understand and make sense of our existence in the cosmos. Philosophers approach the boundaries of the universe from different perspectives, combining scientific understanding with metaphysical and epistemological considerations. These different perspectives show the complexity and uncertainty of thinking about the scope and boundaries of the world. From a metaphysical perspective, philosophers question whether the universe has physical boundaries. Others say that the universe is infinite and expanding in space and time. This perspective is based on the idea that there is no finite space in the universe, but an infinite space with no environment. This perspective challenges our limited minds in trying to understand the concept of infinity and raises questions about the nature of the universe. What does it mean that the universe is infinite? How does this affect our understanding of the world and reality? However, some philosophical interpretations view the world as closed and finite. In a closed universe, space is like the surface of an inversely curved circle. In fact, if you travel far in a straight line, you will return to your starting point. This model, supported by some interpretations of the general theory of relativity, blurs the line between boundaries and the absence of boundaries, suggesting that any boundary is a feature of perception rather than physical reality. From an epistemological perspective, philosophers are concerned with the limits of human knowledge about the boundaries of the universe. Our understanding is limited by observed phenomena and the limits of our instruments. The observable universe, defined by the farthest distances from which light has had time to reach us since the Big Bang, acts as a horizon beyond which we cannot see because of the finite speed of light. However, the true size of the universe may be much larger than this observed portion, introducing an element of uncertainty. Philosophers such as Immanuel Kant argued that our understanding of space and time is limited by the structures of human consciousness, suggesting the finite nature and boundaries of the universe are beyond our comprehension. Conceptual boundaries are another important aspect of theory. Thoughtful discourse is an examination of the limitations imposed by our conceptual and linguistic frameworks. The definition of the world determines our understanding of its boundaries. For example, if the universe is defined as everything that exists, then by definition, it cannot have an outer boundary, because there is nothing beyond everything. This leads to the contemplative question: can anything lie beyond the universe, or does the universe inherently include all things? In cosmology, the idea of a multiverse introduces another layer of complexity. If our universe is only one of many, then the boundaries of our universe may not be defined in absolute terms, but relative to other universes. Philosophers then ponder the implications of the interaction or lack thereof between these universes, and what this means for the concept of a cosmic boundary. Philosophers define the boundaries of the universe through various lenses, considering infinite and finite models, the limits of human cognition, conceptual frameworks, and the possibility of a multiverse. All of these perspectives reveal the deep nuances of meditation on the limits of the world, and combine practical insights with profound metaphysical and epistemological reflections. The question of what is beyond the world, when the world is considered to be all that exists, is a question that contains a profound paradox. At first glance, this may seem strange. If everything is inside the world, then by definition, there is nothing outside. However, this question forces us to think deeply about the nature of life, the limits of our understanding, and the framework we use to describe reality. From a metaphysical perspective, when people think about what lies beyond the universe, they are often subject to the limitations of space and time as we know them. The universe is a collection of space, time, matter, and energy. The idea of something outside of everything challenges our notions of space and boundaries. Philosophers might argue that extraterrestrial speech is a fallacy, an attempt to use spatial metaphors that go beyond meaning. Consider the analogy of a two-dimensional object sitting on the surface of a sphere, such as flat Earth on the surface of a balloon. For this being, there are no boundaries to its two-dimensional universe. Such a question of what lies beyond the universe may reflect our three-dimensional limitations, while the actual nature of existence may be beyond our comprehension. In theology and philosophy, some traditions and thinkers believe that what lies beyond the universe may be something intangible or beyond physical existence, such as a realm of pure abstraction, consciousness, or divinity. For example, some religious views might argue that God or a divine realm exists outside the universe, unconstrained by physical dimensions. This appearance is not spatial, but ontological, representing a fundamentally different reality that interacts with the universe in profound but non-spatial ways. Scientifically, the idea of a multiverse opens up intriguing possibilities. The term multiverse refers to the notion that our universe may be one of many, each governed by different laws of physics, dimensions, or constants. In this context, beyond the universe may be other separate universes within an overarching multiverse structure. In this case, the universe is transformed from a totality of existence to one component of a larger structure. Epistemologically, the question of what lies beyond the universe often reflects the limits of human knowledge and language. Immanuel Kant, for example, argued that human cognition is organized in such a way that we can never know the thing in itself, das Ding an sich, suggesting that some aspects of reality, including perhaps what lies beyond the universe, are beyond human comprehension. This question pushes the boundaries of our conceptual and perceptual limitations, emphasizing the intrinsic limitations of our framework for understanding existence. The question of what lies beyond the universe challenges our conceptions of space, existence, and reality. This raises and epistemological questions that probe the limits of human understanding, suggesting that some questions may be beyond our current ability to fully understand or articulate. This question evokes a rich range of interpretations, combining scientific curiosity with deep philosophical and theological reflections on the nature of reality itself. Philosophical views have historically played a crucial role in shaping scientific theories about the universe, influencing the development of key concepts, methodologies, and interpretation of empirical data. The interaction between philosophy and science is dynamic, with philosophical questions and frameworks both guiding and challenging scientific inquiry. Here are some ways in which philosophical views have influenced scientific theories about the universe. Philosophical views often serve as the conceptual foundation upon which scientific theories are built. For example, the notion of natural laws governing the universe, a cornerstone of modern science, is rooted in philosophical thought. The idea that the universe functions according to consistent and discoverable laws dates back to ancient Greek philosophers such as Aristotle and Pythagoras, and then to Enlightenment thinkers such as Newton and Descartes, who framed their scientific investigations within a philosophical context that emphasized order and rationality. The meaning of knowledge raises fundamental questions about the nature of knowledge and the means by which we acquire it. Epistemological ideas in philosophy have had a significant impact on the scientific method. For example, Karl Popper's work on falsifiability as a criterion for scientific theories influenced hypothesis testing and verification in science. Popper's philosophy was that for a theory to be scientific, it must be falsifiable, an idea that has become central to scientific verification. The interpretation of scientific data goes beyond visual and theoretical observations. The Copenhagen interpretation of quantum mechanics, developed by Niels Bohr and Werner Heisenberg, included important philosophical ideas about the nature of reality, observation, and measurement. According to this interpretation, physical systems do not possess properties until they are measured. The concept is profound, and there is much debate about the nature of reality. Theoretical inquiry into the basic nature of reality is often the driving force behind scientific research. Equally prevalent in the scientific world are questions about the origin, creation, and end of the universe. Theories such as the Big Bang Theory, general relativity theory, and quantum mechanics raise profound metaphysical questions. For example, Einstein's general theory of relativity, which describes the curvature of space-time due to mass and energy, was influenced by his philosophical beliefs about the nature of space and time. Philosophical views also help guide ethical considerations in science, especially when scientific discoveries have profound implications for society. The development and use of nuclear technology, genetic engineering, and artificial intelligence are areas where philosophical ethics intersects with scientific progress, guiding the responsible and ethical application of scientific knowledge. Philosophers often conduct thought experiments to explore theoretical concepts, and this practice has been adopted by scientists as well. Thought experiments, such as Schrödinger's cat in quantum mechanics or Einstein's mental experiments in relativity theory, are powerful tools for clarifying complex theories and exploring their implications. These mental exercises often serve to question, refine, and deepen scientific understanding. Philosophical perspectives constantly challenge scientific theories, pushing the boundaries of current understanding and suggesting new lines of inquiry. For example, the philosophical critique of the completeness of quantum mechanics by scientists such as Einstein, Podolsky, and Rosen, the EPR paradox, has led to significant advances in the field, such as the development of quantum entanglement theory and Bell's theorem. Philosophical views profoundly influence scientific theories about the universe by providing foundational concepts, guiding methodologies, and shaping the interpretation of empirical data. Philosophy forces science to consider broader questions about the nature of reality, knowledge, and existence, fostering a strong and dynamic relationship that drives the search for understanding of the cosmos. This symbiotic relationship demonstrates the importance of interdisciplinary thinking in the search for truth and knowledge about the world. Imagine you have reached the edge of the world. What lies beyond? This is a frightening question that takes us to the edge of human understanding, and perhaps beyond it. According to conventional science, the universe is expanding like an inflated balloon, with each galaxy representing a point on the surface. If you go too far, you think you will reach the edge, but you are stuck in a loop, as if you are walking on the surface of the world without touching the edge. This idea, wrapped up in the geometry of space-time, suggests that searching for physical boundaries is a futile endeavor. The world may be finite or infinite, depending on our place in the universe. These theories raise profound questions. If the universe had no surface and was infinite in shape, where would we be? Are we just a speck in the infinite ocean of the universe? Furthermore, if there are boundaries or sets, does that mean there are other realities, perhaps other parts of us? These tendencies expand the imagination and question the meaning of existence. This idea of being at the edge of the universe forces us to face the limits of our knowledge and question the nature of reality, pushing the boundaries of knowledge and thinking. Exploring the edge of the world expands our understanding and creates a map of the world. Dark matter and dark energy are two of the deepest mysteries of modern cosmology. They are invisible and undetectable by conventional means, but their presence can be determined by their gravitational effects and their influence on the expansion of the universe. Together, they make up about 95% of the total mass and energy of the universe, with dark matter accounting for about 27% and dark energy for about 68%, and ordinary matter, everything we can see and interact with, making up only a small fraction. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it completely invisible to electromagnetic radiation and thus extremely difficult to detect directly. Its existence was first hypothesized in the 1930s by Swiss astronomer Fritz Zwicky. He observed that galaxies within clusters move at speeds that suggest the presence of much more mass than can be accounted for by visible matter alone. Since then, additional data from galaxy rotation curves, gravitational lensing, and the cosmic microwave background radiation have confirmed the existence of dark matter. Despite its invisibility, dark matter exerts a gravitational influence, affecting the structure and formation of galaxies and galaxy clusters. It acts as a cosmic framework around which visible matter accumulates and forms the large-scale structures observed in the universe. Dark energy, on the other hand, is the mysterious force that drives the accelerated expansion of the universe. The discovery of dark energy in the late 1990s came as a significant surprise to astronomers, who had expected that the expansion of the universe might be slowed by the gravitational pull of its contents. Instead, observations of distant supernovae have shown that galaxies are moving away from each other at an accelerating rate. Dark energy is believed to be a property of space itself, uniformly distributed throughout the universe and not diminishing as space expands. Its nature is even less understood than that of dark matter, and it poses a fundamental challenge to our understanding of the laws of physics because it does not fit into the standard model of particle physics or general relativity. Dark matter, which makes up about 27% of the universe, interacts with ordinary matter through gravity. It does not emit, absorb, or reflect light, making it invisible and detectable only through gravitational influence. The presence of dark matter can be inferred from its gravitational attraction to galaxies and galaxy clusters, affecting their rotation rate and distribution. This invisible matter acts as a cosmic framework, providing the gravity necessary for galaxies to form and cluster. In the early universe, the gravitational attraction of dark matter helped to amplify small inhomogeneities left by quantum fluctuations, leading to the formation of large-scale structures such as galaxies and galaxy clusters. These structures create potential wells within which ordinary matter can collect and cool, leading to star formation and the subsequent synthesis of heavier elements through nucleosynthesis in stars. Dark energy, on the other hand, makes up about 68% of the universe and is believed to be responsible for its accelerated expansion. Unlike dark matter, dark energy is not clustered but is uniformly distributed throughout space, exerting a repulsive force that counteracts gravity. The exact nature of dark energy remains one of the biggest mysteries in physics, but its effect on the expansion rate of the universe has critical implications for particle formation and cosmic evolution. Accelerated expansion affects the density and temperature of the universe over time, affecting the rate at which structures form and evolve. This expansion affects the cooling of the universe and the regions where particles can combine to form atoms, molecules, and eventually stars and galaxies. Supersymmetry, often abbreviated as SUSY, is a theoretical framework in particle physics that proposes a type of symmetry between two fundamental classes of particles: bosons, which carry forces, and fermions, which make up matter. According to supersymmetry, for every boson in the Standard Model, there is a corresponding fermionic partner, and vice versa, which has not yet been observed. These partner particles are known as superpartners, whose names repeat the names of their counterparts in the Standard Model, but with the addition of prefixes or suffixes, e.g., squarks are superpartners of quarks, and selectrons are superpartners of electrons. The appeal of supersymmetry is that it has the potential to resolve several unresolved issues within the Standard Model of particle physics and cosmology. One of the most important problems that supersymmetry aims to solve is the hierarchy problem associated with the huge difference in the strength of the gravitational force and other fundamental forces. Supersymmetry suggests that new symmetries in the laws of physics can stabilize the mass of the Higgs boson against quantum corrections that might otherwise make it much heavier, which provides a natural explanation for the weak weights and mass stability of the Higgs boson. Moreover, supersymmetry is the leading candidate for explaining dark matter, a mysterious substance that makes up about 27% of the universe but does not emit, absorb, or reflect light. Supersymmetric particles, especially the lightest supersymmetric particle, the LSP, are stable, electrically neutral, and weakly interact with each other, making them excellent candidates for dark matter. If these particles exist, they can explain the gravitational effects attributed to dark matter in galaxies and galaxy clusters. Despite the elegant theoretical rationale and the convincing solutions it offers for some of the most difficult questions in physics, no direct evidence for the existence of supersymmetry has yet been found. Particle gas pedals, such as the Large Hadron Collider, LHC, at CERN, are conducting extensive searches for superpartners of known particles. However, at the time of my last update, these efforts had not yet led to the discovery of supersymmetric particles, which has led to increased constraints on supersymmetric models, and pushed the predicted masses of superpartners to large values that are beyond the reach of current experiments. Are there theories suggesting that the particles are outside the Standard Model? There are several compelling theories suggesting the existence of particles other than those described in the Standard Model of particle physics. These theories attempt to address the limitations of the Standard Model and issues such as the nature of dark matter, the hierarchy problem, and the unification of forces. The best-known theories are supersymmetry, SUSY, string theory, and theories with extra dimensions. Supersymmetry, as mentioned earlier, extends the standard model by adding a superpartner to each particle, effectively doubling the size of the particle. These superpartners, which have not yet been observed, could help explain the mystery of dark matter and offer a solution to the hierarchy problem by stabilizing the mass of the Higgs boson. Supersymmetry predicts a number of new particles such as gluino, the superpartner of the gluon, and gravitino, the superpartner of the graviton, a hypothetical particle associated with gravity. String theory, another leading candidate for expanding our understanding of the fundamental constituents of the universe, proposes that elementary particles are not point-like points, but tiny vibrating strings. The vibrational modes of these strings correspond to different particles, and their vibrations determine the properties of the particles. String theory inherently incorporates supersymmetry and predicts the existence of many new particles, including those responsible for gravity, potentially offering a way to unify all fundamental forces. It also suggests that there are spatial dimensions in addition to the usual three. Theories of extra dimensions, such as those proposed in various formulations of string theory and approaches such as the brane world scenario, suggest that our universe may have more than just the three spatial dimensions we perceive. These extra dimensions may be packed and hidden at scales too small to be directly detectable with current experiments. Particles can propagate through these extra dimensions, which could explain why gravity is much weaker than other fundamental forces, and it assumes the existence of particles associated with these dimensions. Another approach involves grand unification theories, which seek to unify the electromagnetic, weak and strong nuclear forces into a single force by introducing additional symmetry groups. These theories predict the existence of new particles, such as heavy-gauge bosons, that may mediate transitions between quarks and leptons, turning one type of particle into another. While these theories are mathematically elegant and offer exciting solutions to standard model shortcomings, direct experimental evidence for the existence of particles outside the standard model remains elusive. Particle gas pedals, such as the Large Hadron Collider, are at the forefront of the search for these hypothesized particles. Their discovery would not only confirm these theories, but would fundamentally change our understanding of the fundamental structure and forces of the universe. Gravity, the weakest yet largest of the four fundamental forces, has a profound effect on particle formation, shaping the cosmos from the smallest scales to immense galactic structures. Although its influence is subtle in the field of particle physics, the role of gravity becomes more significant when we consider the broader context of the evolution of the universe and the formation of structures within it. The most direct effect of gravity on particle formation can be observed in star formation. When huge clouds of gas and dust in galaxies collapse under their own gravity, dense regions form within them, creating conditions favorable for nuclear fusion. The intense pressure and temperature in the cores of these nascent stars initiate the fusion of hydrogen atoms into helium, releasing energy in the process. This fusion, the heart of stellar nucleosynthesis, generates the heavier elements necessary for life and the diversity of chemical elements found throughout the universe. Gravity plays an important role in the formation of black holes, regions of space-time where the gravitational forces are so strong that nothing, not even light, can escape them. In extreme conditions near the event horizon of a black hole, theoretical processes such as Hawking radiation predict the creation of particle-antiparticle pairs from the very vacuum of space. While one particle falls into a black hole, another flies out, suggesting an exciting interaction between gravity and quantum mechanics that can influence particle formation. On a cosmological scale, the role of gravity in particle formation extends to the very structure of the universe. The distribution of matter, from the thread-like structures that make up the cosmic web to the formation of galaxies and galaxy clusters is governed by gravitational attraction. This distribution, in turn, determines the regions where particles can clump together to form stars, planets, and other astronomical bodies. Although on small scales, the direct effect of gravity on the behavior of individual particles is overshadowed by the more powerful electromagnetic and nuclear forces, its cumulative effect on cosmic timescales and distances is crucial to understanding the evolution of the universe. The formation of particles, stars, and galaxies, and the very structure of the cosmos are all evidence for the fundamental role of gravity in shaping the universe from its earliest moments to the present day. Inflation theory is a key concept in cosmology that addresses some of the most fundamental questions about the early universe. Proposed in the early 1980s by physicists including Alan Guth and Andre Linder, inflation suggests that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion. This rapid expansion, far exceeding the speed of light, has increased the size of the universe by many orders of magnitude in the blink of an eye. Inflation was introduced to address several problems inherent in the Big Bang theory as it existed at the time. One of these is the horizon problem, which raises the question of how parts of the universe that are now widely separated could have been at the same temperature if light has not had time to travel between them since the universe's inception. Inflation explains that these regions were once close together and then were pushed apart by rapid expansion, allowing them to come to thermal equilibrium before they were separated beyond the horizon of causality. Another issue that inflation addresses is the flatness problem. Observations show that the universe is remarkably flat. That is, it conforms to the geometry described by Euclidean geometry on large scales, which requires fine-tuning of the initial conditions if the universe were to expand at a constant rate after the Big Bang. Inflation elegantly solves this problem by blurring any curvature in the fabric of the early universe. This causes the universe to appear flat on large scales, which is what is observed. Inflation also provides an explanation for the origin of the large-scale structure of the universe. The theory predicts that tiny quantum fluctuations in the early universe were stretched to astronomical scales by inflationary expansion. These fluctuations then served as seeds for the growth of structures in the universe, such as galaxies and galaxy clusters, through gravitational attraction. Inflation theory is supported by observations of the cosmic microwave background radiation, the afterglow of the Big Bang, in which small temperature fluctuations are observed, consistent with the predictions of inflation. These observations have cemented inflation as a cornerstone of our understanding of the early universe, even though this theory pushes the boundaries of modern physics. Although inflation theory has greatly expanded our understanding of the early moments of the cosmos, it also raises new questions, such as what caused inflation to begin and what stopped it. Various models of inflation have been proposed, some of which incorporate ideas from quantum field theory and string theory, in an attempt to provide a more complete picture of these dynamics. So how does inflation explain the uniformity of the cosmic microwave background? Inflationary theory offers a compelling explanation for the homogeneity observed in the cosmic microwave background, CMB, a weak afterglow of radiation that permeates the universe after the Big Bang. The CMB represents a nearly uniform temperature across the sky, with incredibly small variations, about 1 part in 100,000. This homogeneity, combined with isotropy, the sameness in all directions of the universe on large scales, presented a serious mystery to cosmologists before the advent of inflationary theory. Given the vastness of the universe and the finite speed of light, regions on opposite sides of the observable universe have not had enough time since the Big Bang to exchange heat or light and come to thermal equilibrium. This dilemma, known as the horizon problem, has raised questions about how the CMB can be so remarkably uniform. Inflation solves this puzzle by proposing a period of exponential expansion shortly after the Big Bang. According to inflationary theory, the observable universe expanded from tiny subatomic size to macroscopic size in less than a trillionth of a second. This rapid expansion means that regions now on opposite sides of the observable universe were once close together, within causal contact, before inflation separated them. These regions were able to come to thermal equilibrium by exchanging energy and smoothing out temperature differences before being stretched across the sky by inflation. Thus, when we look at the CMB, we see a snapshot of a much smaller homogeneous universe stretched across the vastness of space, which explains its uniform temperature. The small temperature fluctuations we observe in the MDB are explained by quantum fluctuations in the density of the universe that were present just before inflation. These fluctuations, once minuscule, were amplified by the inflationary expansion and spread to cosmic scales, forming the seeds of the large-scale structure of the universe, such as galaxies and galaxy clusters. The patterns of these fluctuations in the CMB have been accurately measured by experiments such as the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, providing strong support for the inflationary model. Antimatter is a fundamental concept that mirrors the properties of matter, but with opposite charges. For every type of particle that makes up matter, there is a corresponding antiparticle that makes up antimatter. These antiparticles have the same mass as their matter counterparts, but have opposite electric charge and different quantum numbers. The most famous examples are the positron, the antiparticle of the electron, the antiproton, which carries a positive charge, and the antiproton, which has the same mass as the proton but a negative charge. The existence of antimatter was first predicted by British physicist Paul Dirac in 1928, based on his work on expanding the equations of quantum mechanics to take into account the theory of special relativity. Dirac's equations assumed the existence of particles that have the same mass as electrons but opposite charge. This prediction was confirmed in 1932 when Carl Anderson discovered the positron. This discovery was revolutionary because it provided the first evidence for the existence of antimatter and confirmed Dirac's theoretical framework. When a particle of matter collides with an equivalent antiparticle, they annihilate each other in an energy explosion, usually producing gamma rays. This annihilation process shows the equivalence of mass and energy described by Einstein's MPMC quadratic equation, and is an integral part of the interaction between antimatter and matter. Antimatter is not just a theoretical curiosity, it has practical applications and significance. In medicine, for example, positron emission tomography, PET, is based on the detection of gamma rays from positron annihilation to create detailed images of the body. In addition, understanding antimatter is crucial to advancing our knowledge of the universe. Cosmologists study antimatter to answer fundamental questions about the Big Bang and why the observable universe is composed almost entirely of matter. Despite theories predicting that equal amounts of matter and antimatter formed in the early moments of the universe. The study of antimatter is also pushing the boundaries of particle physics by challenging scientists to create, capture, and study antiparticles in the laboratory. For example, experiments with antihydrogen atoms aim to compare the properties of hydrogen and antihydrogen to test the fundamental symmetries of nature. This research could open up new physics beyond the standard model, providing insight into the forces and particles that shape our universe. Now let's talk a bit about the CP violation and how it relates to the matter-antimatter asymmetry. CP violation refers to a fundamental phenomenon in elementary particle physics, where the interaction of charge conjugation C and parity inversion P is not conserved. Simplistically, This means that the processes of transformation of some particles into corresponding antiparticles proceed differently when charges and spatial orientation are changed. CP violation is very important for understanding the matter-antimatter asymmetry in the universe. In the early universe, matter and antimatter were produced in nearly equal amounts during particle-antiparticle creation processes. However, if all physical processes perfectly observed CP symmetry, matter and antimatter would completely annihilate each other, leaving behind a universe devoid of matter. The observed asymmetry of matter and antimatter suggests that there must exist processes in which CP symmetry is broken, favoring the production of matter over antimatter. This violation of CP symmetry allows for subtle differences in the behavior of particles and antiparticles, resulting in a small excess of matter that ultimately produce the structures we see in the universe today. CP violation has been experimentally observed in some rare elementary particle decays such as neutral kaons and B mesons. These experiments have provided insight into the mechanisms responsible for creating the matter-antimatter asymmetry in the early universe. However, the exact cause of CP violation and its relation to the observed matter-antimatter asymmetry are still active areas of research in particle physics. Do we really understand the origin of the universe? This question has puzzled scientists, philosophers, and theologians for centuries. Delving deeper into the depths of cosmology and elementary particle physics, we find glimpses of the cosmic drama that unfolded billions of years ago. Despite our best efforts, the final birth of the cosmos is shrouded in mystery. Theories like the Big Bang provide a framework for understanding the evolution of the universe from the earliest moments of its existence. But when we look at the moment of creation, we encounter a realm where the laws of physics are broken and our common understanding crumbles. It is a realm of extreme temperatures, densities, and energies where profound changes are taking place in the fabric of space-time. In our quest to understand the origins of the universe, we face the limitations of human knowledge and scientific research. Can we ever hope to unravel the mysteries of existence with our limited intellect and empirical methods? Are there areas of knowledge beyond human understanding? Some argue that the desire to understand is an inherent part of human nature that drives us to explore, ask questions, and seek answers to the deepest mysteries of existence. Others argue that there is a limit to what we can know, and that some aspects of reality may forever remain beyond our comprehension. How does the concept of something fit into modern physics? This question challenges our fundamental understanding of reality. From the perspective of modern physics, nothingness is simply the absence of matter or energy. On the contrary, it is a complex and dynamic landscape governed by the laws of quantum mechanics. In quantum physics, the cosmic vacuum is far from nothing. It is full of virtual particles that appear and disappear spontaneously, borrowing energy from the void for a moment before annihilating each other. This phenomenon, known as vacuum fluctuations, indicates that even in the absence of particles, the fabric of space-time is buzzing with activity. Moreover, the concept of nothingness is intertwined with the mysteries of the origin of the universe. The Big Bang theory posits that the universe emerged from a singularity, a point of infinite density and temperature. But what preceded the Big Bang? Did anything actually exist before the expansion of the universe? Or are there dimensions of existence beyond our current understanding? Research in particle physics has far-reaching implications that go beyond laboratory studies and have many benefits for society. While the topic may seem esoteric, advances in particle physics are producing tangible results that affect our daily lives. One of the important contributions of particle physics research is its role in medical imaging and therapy. Technologies such as PET, positron emission tomography, and MRI, magnetic resonance imaging, have emerged from the study of particle physics. These imaging techniques are critical to the diagnosis and treatment of disease, improving the health of millions of people around the world. In addition, particle physics has paved the way for improved radiation therapy in the treatment of cancer. Techniques such as proton therapy, which uses beams of protons to precisely target tumors with minimal damage to surrounding healthy tissue, have emerged from particle physics research. These techniques offer more effective and less invasive treatment options for cancer patients. Research in particle physics has contributed to the development of innovative materials and technologies. For example, the World Wide Web, invented at CERN to facilitate communication between researchers, has changed the way information is accessed and shared globally. In addition, advances in particle detector technology have led to more sensitive detectors used for safety testing, environmental monitoring, and even archaeological research. The search for fundamental knowledge in particle physics often stimulates progress in other fields as well. Collaborations among physicists, engineers, and mathematicians foster interdisciplinary research that promotes innovation in many different fields. Future discoveries in particle physics promise to change many aspects of our daily lives. While some of these advances may seem distant or abstract, their potential impact on society can be profound. One area where future discoveries could have a significant impact is energy production and storage. Breakthroughs in particle physics can lead to the development of more efficient and sustainable energy sources, helping to address pressing issues such as climate change and energy security. For example, advances in fusion energy, inspired by the study of plasma physics in particle gas petals, may one day provide a clean and virtually limitless source of energy. Discoveries in particle physics can lead to advances in technology and computing. The development of quantum computing, which relies heavily on the principles of quantum mechanics studied in particle physics, could revolutionize fields such as cryptography, drug discovery, and artificial intelligence. Quantum computers can solve complex problems exponentially faster than classical computers, opening up new opportunities for scientific research and innovation. While the study of particle physics offers great potential for scientific progress, it also raises a number of ethical considerations that require careful consideration. One such aspect is resource allocation. Particle physics experiments often require significant financial investment and access to advanced technology. Critics argue that these resources could be used to solve pressing social problems such as poverty, health, and education. Proponents of quantum computing, however, argue that investments in basic research can lead to unexpected technological breakthroughs and long-term social benefits. Another ethical concern is the safety of particle physics experiments, especially those involving high-energy particle gas petals. While the likelihood of catastrophic events resulting from these experiments is extremely low, some worry about potential risks, such as the creation of micro-black holes or the release of dangerous radiation. Researchers and regulators must carefully assess and mitigate these risks to ensure the safety of both experimental participants and the public. There are ethical considerations associated with the dissemination of knowledge and the potential misuse of scientific discoveries. Particle physics research often provides valuable insights into the fundamental workings of the universe, which can have broad implications for technology, medicine, and other fields. However, there is a risk that this knowledge could be weaponized or used for harmful purposes. Scientists and policymakers must consider how to balance the benefits of scientific progress with the need to prevent misuse and ensure responsible knowledge management. In addition, there are ethical issues associated with international collaboration and dissemination of particle physics research. Collaborative efforts between scientists from different countries are essential to advance knowledge in this area. However, issues such as intellectual property rights, data sharing, and fair access to research opportunities can arise, especially where resources are limited or there are differences between countries. Ensuring honest and transparent collaboration is essential to upholding the principles of scientific integrity and promoting global progress. While particle physics research holds tremendous promise for scientific discovery and technological innovation, it also presents complex ethical challenges that must be addressed thoughtfully and responsibly. With these ethical considerations in mind, and with an open dialogue, scientists, policymakers, and society at large can work together to overcome the ethical challenges of particle physics research and maximize the benefits to humanity. As we conclude our journey in reflecting on the emergence of particles from seemingly nothingness, we are confronted with profound philosophical questions that go beyond empirical science. Perhaps in the cosmic symphony of creation lies a deeper truth beyond our current understanding, a truth that speaks to the interconnectedness of all things and the infinite potential embedded in the fabric of reality. Could it be that particles emerge not from the void, but from the limitless reservoir of possibilities that permeates the cosmos? Ultimately, the question of how particles form from nothing forces us to consider our place in the vastness of the universe and to embrace the wonder and mystery that surrounds us. This challenges us to expand our consciousness beyond conventional thinking and embrace the limitless possibilities underlying existence. How do you think particles came into being? How did it all begin? Share your thoughts in the comments below. Thank you for watching.
When we look up at the night sky, we see only a small part of what the universe hides. The part we can see is called the visible universe. And that's really all that our eyes or the most powerful telescopes can see. But imagine for a moment that beyond those twinkling dots of stars, there could be something else, something incomprehensibly great and mysterious. And that's where scientists enter the arena with their most exciting hypotheses about what lies beyond our cosmic horizon. Tonight, we're going to try to explore 5 of the boldest and craziest of them all. Brace yourselves. We are taking a journey beyond the visible to discover the unknown. We're talking about something that sounds like science fiction, but is actually serious scientific research: the Hubble sphere and the possibility of our cosmic twin. The Hubble sphere is the boundary of the universe beyond which objects are moving away from us at speeds faster than the speed of light. It's not that they're traveling faster than light. Rather, it's the space between them and their subjects that is expanding so rapidly. Now imagine that beyond this world, there is another universe with a planet like Earth and inhabited by someone very much like you. The science sounds crazy, but math and physics tell us that anything is possible in an infinite universe. If the universe is truly infinite, there must be duplicates of us out there somewhere. This idea is based on the assumption that if the universe is infinite and contains an infinite number of galaxies, then the combinations of particles that make up our world must repeat somewhere, which means that somewhere in the vast expanse of space there is another person watching this video, but perhaps in another universe. Of course, this is just a hypothesis and can't be proven yet, but it does encourage us to consider how big our universe is. Perhaps one day, when science reaches new heights, we will learn more about what lies beyond the Hubble sphere, and perhaps even find our cosmic counterparts. At present, we can only speculate and dream about the infinite possibilities of the cosmos. Now, we're going to talk about the most exciting and perhaps the most fantastic hypothesis: the multiverse hypothesis. Imagine that our universe is just one of countless coexisting universes. These universes could be completely different, with different laws of physics, different initial conditions, or even contain completely different life forms. For example, in one parallel universe, Earth could be a planet where the dinosaurs did not die out, but continued to evolve, becoming the dominant intelligent life form. In another case, the gravitational constant could be so small that stars could not form, and the universe would remain a dark and cold place without light. According to the hypothesis, the multiverse can be divided into different levels. At the first level, there are universes that are just beyond our visible horizon, and in which the same physical laws that apply to us may apply. At the second level, there are universes with different physical constants. The third level represents universes created in the many worlds interpretation of quantum mechanics, where each quantum event creates a new universe. Finally, the fourth level. It contains all mathematically possible universes. One of the most interesting ideas of the multiverse. This suggests that some of them may have a version of us living a completely different life. Perhaps there is someone among you who has become an astronaut and explores distant galaxies. Or you, who never knew what the internet was. And now he's trying to club some wild boar for his evening meal. So, now let's dive into the world of parallel universes, which has recently been beautifully presented in the new TV series Dark Matter. This series, based on the novel of the same name by Blake Crouch, tells the story of a physicist named Jason who finds himself in an alternate version of his life. To get back to his family, he has to go through a series of parallel realities and face an alternate version of himself. This series illustrates one of the most intriguing ideas in physics and philosophy: the possibility of multiple universes, each of which is a reflection of the different paths our reality could take. In each of these universes, the story unfolds differently, depending on choices and coincidences that shape the unique course of events. The theory of parallel universes suggests that for every possible outcome of events in our universe, there is a separate universe in which that outcome occurred. This means that there may exist a universe in which you made another major decision that led to a completely different life. You may have never met your best friend in any of these universes. In the second, you invented something that changed the world. Stephen Hawking, one of the greatest minds of our time, has also contributed to the development of this theory. In his latest work, he proposed a way to solve the cosmic paradox of parallel universes and suggested that some of these universes may be very similar to our own. Dark Matter shows how these alternate realities can intersect and interact, giving viewers a unique insight into how events might unfold if the past was different. It makes you think about how fragile and changeable our reality can be, and how small changes can lead to completely different outcomes. So what's going to happen? It turns out that each of us is the center of our own universe, and every choice we make creates a new story. Imagine you are standing at the edge of a vast, vast ocean. You can see the waves reach the horizon, but what lies beyond it? It's the same with the universe. We see stars, galaxies, nebulae, but what lies beyond the cosmic horizon? Maybe there's just nothing out there. This thought may seem strange, for how can nothingness exist? But in cosmology, nothingness necessarily means the total absence of everything. It could be a space without matter, radiation, galaxies, or nothingness in the absolute sense of the word. But even in this vacuum, there can be quantum fluctuations, virtual particles that appear and disappear in the blink of an eye. According to one theory, there may be an infinite void beyond the observable universe. This assumption is based on the fact that the universe is expanding, and with each passing second, the boundary of the observable universe is moving farther and farther away from us? If so, then perhaps there really is nothing beyond our visible horizon. No stars, no galaxies, no light. So when we talk about the possibility that there could be nothing beyond the visible universe, we are not talking about just anything. Let's talk about the limits of our imagination and how far we can look into the abyss of space. The universe is not only what we see, but also what we cannot see, and that every new discovery can completely change our perception of reality. This is why the study of space is a wildly interesting thing that keeps us constantly asking questions and searching for answers, even if those answers may not be to our liking or expectations. The dark flow theory predicts that clusters of galaxies in the universe are moving in a coordinated fashion in the same direction. This is not just random motion, but seems to be caused by some massive structure that is beyond the visible universe. Imagine that our entire cosmic home is drawn to an invisible beacon that we can't see, but can feel through its gravitational influence. This theory came about after analyzing data from the Sunyaev-Zel'dovich effect. That allows us to measure the movement of gas in a cluster of galaxies. Scientists have found that these clusters move in a particular direction faster than could be explained by known gravitational forces. One possible explanation for the dark flow is the gravitational influence of objects outside the visible universe. There could be a supercluster of galaxies, or even an entire parallel universe that was connected to ours at the time of the Big Bang. This crazy hypothesis suggests that there may be structures beyond the visible that have a huge effect on everything in visible space. It's as if we've discovered that our universe is just one part of a vast cosmic archipelago, where each island affects the motion and fate of the others. The dark current theory has yet to be definitively confirmed, and scientists continue to study its effects to see if it really exists and what might be causing it. If the dark current does exist, it would be one of the most important discoveries ever. Let's talk about what could happen to our universe in the distant future. It's a story about how things might end up freezing rather than hitting. This is a theory known as the Big Freeze. Imagine a universe that continues to expand until no more stars are born and the last ones die out, leaving behind only dim dwarf stars and black holes. The temperature of the universe tends to absolute zero, and everything in it slows to a complete stop. According to this theory, the universe came into existence as a result of the Big Bang, but instead of eventually returning to its original size, it continues to expand forever. Over time, when all the stars have used up their fuel and no new ones are forming, the universe becomes dark and cold. Energy is distributed so evenly that stars and galaxies can no longer form. Interestingly, this process may not just be a slow decline. For example, scientist Christoph Wetterich hypothesizes that the universe was cold and fragile in the beginning, and that over time, key particles became heavier and the gravitational constant decreased. This assumption explains why our current cosmos is dominated by dark energy and why we see density fluctuations in the early universe. So, if the Big Freeze theory is correct, our universe may not be a boiling cauldron of stars and galaxies, but rather an infinite frozen void, like a giant refrigerator. Here, we have come to the end of our space journey to different parts of the universe. Together, we looked at what was visible beyond the boundary and allowed ourselves to dream about what might be lurking in those distant spaces. We've talked about multiverses, where any one of us could be anything, and a dark flow that may be pulling us towards something we don't understand. We have considered the idea that there can be nothing absolute beyond the cosmic horizon. We have even allowed ourselves to imagine that our universe is just one of an infinite number of stories unfolding in parallel worlds. Who knows, maybe one day we will be able to confirm these hypotheses or even discover new ones that will overturn our established knowledge. And while we wait for these great discoveries, let's keep asking questions, searching for answers, and enjoying every moment of our marvelous cosmic adventure. After all, curiosity is what makes us human and allows us to dream the impossible. We live in an age of great astronomical discoveries. Thanks to modern orbiting telescopes, we already know more than 5,000 distant worlds. Most of them are really amazing places, unique and mysterious, and sometimes even very dangerous. There are planets illuminated by the light of 2 or 3 lamps at a time, and there are those that are forever hidden in the cosmic darkness. Some of them are terrifying in their extreme conditions, and others are surprising in their unusualness. We've traveled to some of the most terrifying exoplanets in the past. It's time to continue your journey. Among a number of other worlds, special attention is usually paid either to potentially habitable planets with comfortable conditions and moderate climate, or on the contrary, very dangerous objects that stand out from the general background. However, there is a third category. These are anomalous celestial bodies that exhibit strange behavior that is sometimes difficult to explain scientifically. Such objects defy our knowledge and deserve special attention, and the next world belongs to them. 2009. The Kepler-413 system environment. An unknown object passes between our planet and a distant star, diminishing its brightness for a moment. Astronomers, who believe this event to be a regular transit of an exoplanet, report the discovery of a new celestial body. High-precision calculations can even determine its parameters. The planet turns out to be a cold giant with a mass of about 25 Earth masses and a radius about 40% that of Jupiter. However, the next expected transit did not occur until 180 days later. The planet, so clearly visible in the old data, seemed to vanish without a trace. The mysterious phenomenon can be explained by a dark spot in the photosphere of the star or a giant field cloud moving near it. But these hypotheses were completely disproved when, after 800 days, the mysterious objects returned as suddenly as it disappeared. The supposed planet eclipsed the disk of its parent star 5 times before disappearing again. However, a clue has already been found. It turns out that Kepler-413b's orbit is very unusual. The celestial body is near the double focus and is 0.36 AU away from the common center of mass of the system. Its orbit is subject to constant gravitational perturbations, and the changing attraction of 2 neighboring stars significantly changes the plane of the orbit, causing cyclic oscillations. When the deviation reaches a maximum, the target leaves the field of view and then returns to it. Calculations show that the orbit of Kepler-413b changes with a period of about 11 years, deviating from the average value of 2.5 degrees in either direction. The planet's own rotation axis also changes its position significantly. Its maximum angle of inclination is 30 degrees. Combined with the marked eccentricity of the orbit and its periodic displacement, this results in a bizarre variation of climatic conditions on the surface. The region receiving the maximum amount of light from the parent star is constantly shifting from the equator to the poles and back again, resulting in dramatic temperature variations. It is likely that this process generates huge hurricanes of planetary scale, the size of which could exceed Jupiter's Great Red Spot. Air currents can carry ice clouds at a speed of several kilometers per second, gradually losing stability and collapsing. Meanwhile, collisions and deformation of vortices are capable of creating grandiose atmospheric emissions, which are able to overcome the gravity of the planet and reach the open space. According to calculations, they spend some time there before being pulled back by gravitational forces. All these incredible phenomena make the planet a very inhospitable place. But even that may seem like a peaceful island compared to the future world. 190 light-years from Earth. System environment HD 806-6. In the vicinity of this yellow dwarf, with parameters remarkably close to the Sun, is a planet with a very variable climate. Like a giant comet, it is rapidly approaching its main target, burned by the hot rays of its corona, or moving away to the periphery of the system. SE is a gas giant with 4 times the mass of Jupiter. The radius is slightly different from that of Jupiter. At the farthest point of its orbit, the planet is 0.88 AU away from its parent body and receives about as much heat from it as the Earth receives from the Sun. It is believed that at present, clouds consisting of water vapor droplets, ice crystals, or even quartz microparticles are condensed in its atmosphere. And the surface temperatures of the gas giant's hypothetical satellites can reach Earth-like values. However, as the planet approaches the star, its conditions change very quickly. In 55 days, the distance between the two decreases by a factor of almost 30, while the energy flow of the star increases by a factor of 800. Observations show that at the lowest point of its orbit, the temperature of the exoplanet increases about 2 times in just 6 hours, from 500 degrees to 1200 degrees. Such sudden changes lead to strong hurricanes that can reach speeds of up to 5 kilometers per second. The atmosphere of the gas giant absorbs an incredible amount of heat and expands so rapidly that it creates shock waves that can circle the entire planet several times. Water vapor breaks down into oxygen and hydrogen under the influence of temperature, and quartz crystals vaporize without leaving a trace, but then condense back into giant sand clouds. HD 80606b appears to be the only planet in its system. The gravity of another nearby star not only changed its orbit, but also brought chaos to the protoplanet's disk. Therefore, the chance of encountering large objects nearby is very small. However, destabilization of a planetary system due to the interaction of celestial bodies is not that rare. 1530 Earth color years. Neighboring regions of the Kepler-36 system. The central object of this system is a yellow subgiant. Its mass is close to the solar mass, and its radius is 62% larger than that of our star. 2 planets, a rocky super-Earth and a hot mini-Neptune, are orbiting rapidly around the star. Every 97 days they come critically close, only 1.9 million kilometers, about 20 times the minimum distance between Earth and Venus. At such times, their mutual attraction becomes the cause of global cataclysms. However, a few days pass and the celestial bodies diverge again until the next resonance. According to calculations, the gravitational interaction between the planets at their maximum approach is about 13 times greater than that between the Earth and the Moon. This effect should be particularly noticeable on the surface of the rocky planet. Its shell can crack and change under titanic forces. Incredibly powerful earthquakes occur. The resulting rifts can be hundreds of kilometers long and cause several giant volcanic eruptions. It is likely that some regions of the planet did not have time to cool down for such a short period of relative calm, and there is always a bubbling sea of hot magma. The reasons for the formation of such an unusual system are still controversial. It is now known that the super-Earth, named Kepler-36b, is located at a distance of 0.12 AU from its parent star and makes a complete revolution around it in 14 days. Its mass is 3.8 times the mass of the Earth, and its radius is 1.5 times the size of our planet. The object is calculated to have a temperature of 980 Kelvin, or just over 700 degrees Celsius, and its average density is about 30% higher than Earth's. Based on this information, it is suggested that the celestial body may be a Croton planet, the core of a gas giant that has lost its atmosphere. Such objects contain many heavy metals, such as iron and lead, as well as sulfur and silicon compounds. It is likely that the light elements that once formed the dense shell of the celestial body could have escaped into space under the influence of the stellar wind. Also, keep in mind the gravitational pull of another planet that can help the process. The name of this object is Kepler-36 Coulomb, and it is believed to belong to the category of hot mini-Neptunes. The celestial body moves in a nearly circular orbit with a radius of 0.13 AU and makes a complete revolution in 16 days. Its mass is 7 times larger than our planet, and its radius is 3.7 times larger than Earth. Because of its proximity, the temperature of the object is also very high at 928 Kelvin, or 655 degrees Celsius. According to current ideas about the structure of exoplanets, this celestial body is surrounded by a dense, multi-layered atmosphere composed mostly of nitrogen, hydrogen, and helium. As the depth increases, the pressure inside the gas shell increases, and it gradually turns into an ocean of supercritical fluid surrounding the solid core. Meanwhile, under certain conditions are possible and truly fantastic phenomena. For example, the gravity of a more massive planet has the potential to take satellites away from its smaller companion, and tidal stress can destroy them to form vast asteroid streams. In addition, the mutual gravitational influence of the two planets deforms their orbits, changing the eccentricity and other parameters. Because of this, the entire system behaves erratically and unpredictably, and its evolution cannot be calculated for any long time. Modeling shows that with 91% probability, both planets will collide with each other within the next 70 million years, generating hundreds of thousands of debris that will scatter throughout the planetary system, thereby further increasing the chaos within it. Perhaps such large-scale cataclysms have already happened more than once in a neighboring system. 434 light-years from Earth. 4 astronomical units from a young sun-like star is a stunning object informally known as Super Saturn. It is a brown dwarf, or a large gas giant, with a mass of about 20 Jupiters. Observations show that it is a young planet, about 15 to 16 million years old, and still forming. Most of its atmosphere consists of hydrogen and helium, and inside is a massive metallic core. This object is surrounded by a system of rings, much like Saturn, but of much more imposing size. No fewer than 37 distinct rings have been identified from the transit. In addition, the outer radius of the largest of them reaches about 0.6 AU. This is comparable to the size of the orbit of Venus, and about 640 times the radius of Saturn's rings. According to calculations, the total mass of the planet's circular disk exceeds that of Earth, and its behavior shows signs of chaos. Mathematical modeling shows that such structures are unstable and gradually collapse. Some of their particles lose speed and fall to the planet. Others, on the contrary, accelerate and leave the saucer for good. However, this process is much longer in time, and may take several 100 million years. Also, in the system of rings, was recorded a large gap with a radius of about 0.4 astronomical units, which is considered indirect evidence of the existence in this area of an exosatellite with a mass of about 80% of the Earth. According to modern ideas about the physics of cosmic bodies, it is such an object that is able to clear its orbit from small debris, forming a wide gap in the ring-shaped structure. In addition to him, observations indicate the presence of at least 2 more celestial bodies, each of which has a mass of about 30% of the Earth's and is located at a distance of about 0.25 astronomical units from the center of the brown dwarf. By analogy with known to us large planets, can be assumed that in total, within the gravitational influence of the central object, can be located several hundred exosatellites, including quite massive. Modeling of such a system, taking into account radiation from the parent star, heat flow from the giant planet, and tidal influences, shows that the temperature of its constituent celestial bodies can approach comfortable values. One can only imagine how fascinating the night sky is from the surface of such an exosatellite. At this distance, the brown dwarf occupies an area of the sky 70 times larger than the full moon, and its soft glow can dispel darkness and turn night into a hazy twilight. Instead of a multitude of stars, huge halos of light cross the planet's sky from horizon to horizon. At the same time, the ejective forces of a nearby massive body could cause many eruptions on the surface of the satellite, and its supposed ocean could cover the Earth with giant waves. The width of the tidal zone in such conditions can reach hundreds of kilometers, which allows us to consider it a unique climatic zone, something between the land and the ocean floor. However, it is worth remembering that such structures tend to be unstable and quickly change their appearance beyond recognition. At present, it is difficult to say how long we will be able to admire the giant rings and what will become of them in millions of years. Deep space is full of mysterious and surprising objects. They appear before us in the form of many photographs and a great deal of information, little by little revealing their secrets to all human curiosity. At the same time, each discovery raises new questions, and that means that the learning never ends.
Observational evidence relating to theories prior to the Big Bang is both intriguing and complicates the picture because it touches on the very nature of the origin of the universe. Although we cannot directly observe conditions before the Big Bang because of the constraints imposed by the event itself, various indirect observations and theoretical models convincingly support or refute ideas about the early state of the universe. One of the most significant pieces of evidence is the cosmic microwave background radiation, relict radiation that fills the universe and represents the afterglow of the Big Bang, supports the idea of a hot, dense state before the expansion of space and time. Measurements of temperature fluctuations in the cosmic microwave background provide a wealth of information about the early universe, including its density, composition, and distribution of matter. Some pre-Big Bang theories, such as inflationary models, emphasize rapid expansion, and observational evidence fits well with these ideas, reinforcing their plausibility. Another important piece of evidence is the large-scale structure of the universe. The distribution of galaxies and galaxy clusters gives an idea of how matter evolved after the Big Bang. Observations of the rate of expansion of the universe, especially through redshift measurements of distant galaxies, show that the universe is expanding. These data support the idea that the universe evolved from a very different state. Some pre-Big Bang models theoretically predict certain patterns of structure formation that can be compared to observed large-scale structures. However, not all observations are in clear agreement with specific theories prior to the Big Bang. Some problems arise from the entropy of the universe. The second law of thermodynamics says that the universe tends to increase in entropy over time. The idea that the universe arose from a highly ordered state prior to the Big Bang raises questions about how this high entropy fits with the observed low entropy conditions. Models proposing oscillating universes or cyclic models attempt to address this problem by assuming that the universe undergoes repeated phases of expansion and contraction, which offers an alternative to a single beginning. Although observations of the cosmic microwave background radiation and the structure of the universe support specific theories prior to the Big Bang, there remain unanswered questions and problems, especially with regard to entropy. Continued study and refinement of these observational data will continue to shape our understanding of the mysterious conditions that preceded the Big Bang. The cosmic microwave background radiation is a crucial piece of evidence that helps us understand the early universe. This surprising phenomenon represents an afterglow from the hot, dense state that existed shortly after the Big Bang, some 380,000 years later, when the universe cooled down enough for protons and electrons to combine to form neutral hydrogen atoms. This process allowed photons to travel freely, marking the moment when the universe became transparent to radiation. The cosmic microwave background serves several key purposes in cosmology. The uniformity of temperature across the sky indicates that the early universe was extremely homogeneous and isotropic as it cooled and transitioned from a hot plasma state. However, small temperature fluctuations are also present, revealing tiny variations in density that would later evolve into the structures we see today, such as galaxies and galaxy clusters. By studying these temperature fluctuations, scientists can gain insight into the initial conditions that led to the formation of the large-scale structure of the universe. In addition, the cosmic microwave background provides crucial information about fundamental cosmological parameters such as the density and composition of the universe. By analyzing its spectrum, researchers can estimate the amount of ordinary matter, dark matter, and dark energy that make up the present-day universe. These measurements have led to significant progress in understanding how these components interact and influence the evolution of the universe. In addition, the cosmic microwave background radiation is important for theoretical models such as inflationary theory. According to this theory, the rapid expansion of the universe occurred early in its history, smoothing out the initial irregularities. The observed fluctuations of the cosmic microwave background confirm the predictions of inflationary models, supporting the idea that this event played a crucial role in shaping the properties of the early universe. The cosmic microwave background radiation is thus a cornerstone of modern cosmology, providing a direct link to conditions that existed shortly after the Big Bang. By continuing to study this relic radiation, scientists are furthering their understanding of the origin, evolution of the universe, and the fundamental forces that shape it. Gravitational waves represent a novel way for scientists to explore the mysteries of the universe, including potential states before the Big Bang. Spawned by some of the most violent and energetic processes in the cosmos, such as the collision of black holes or neutron stars, these ripples in spacetime carry information about their origin that is often not obscured by other interfering light, such as dust and gas. One of the most interesting aspects of gravitational waves, they can encode information about the very early universe, especially during epochs such as cosmic inflation. The rapid exponential expansion of the universe is thought to have occurred during inflation in the fraction of a second after the Big Bang. If gravitational waves originated in this era, their characteristic features can provide insight into the energy scales of inflation, the dynamics of the early universe, and the fundamental physical conditions that existed before the Big Bang. Current and future gravitational wave observatories, such as LIGO and the upcoming LISA Space Observatory, aim to detect these primordial waves. Their detection will not only provide valuable confirmation of inflationary models, but may also indicate the characteristics of the fundamental forces that govern the evolution of the universe during that period. For example, gravitational waves can indicate a potential energy landscape driving inflation, and even hint at certain symmetries in physical laws that may have existed. In addition, researchers are investigating whether gravitational waves may contain clues about the transition from the quantum realm to classical behavior in the very early universe. How the universe emerged from this quantum state and how spacetime itself was transformed can also be accessed through gravitational waves, helping to bridge the gap between quantum mechanics and general relativity. Gravitational waves have the potential to provide deep insights into conditions that existed before the Big Bang. By studying these ripples in spacetime, scientists will be able to unravel fundamental questions about the origin of the universe, the mechanisms that governed its rapid expansion, and the very nature of the forces that shaped our cosmos. As detection capabilities develop, gravitational waves may open new windows into the early history of the universe, expanding our knowledge beyond current observations. Testing theories about conditions before the Big Bang presents a unique challenge because we face constraints dictated by both the nature of the Big Bang itself and the field of modern physics, which includes quantum mechanics and general relativity. However, scientists use different observational strategies, theoretical frameworks, and experimental techniques to study these mysterious conditions. One approach involves studying the cosmic microwave background radiation, which picks up echoes of the universe shortly after the Big Bang. By analyzing temperature fluctuations, cosmologists can extrapolate details about the dynamics of the early universe, offering indirect evidence that provides a basis for theories that predate the Big Bang. These observations may help confirm or refute models of cosmic inflation or other scenarios that suggest special conditions preceding the Big Bang. Data from instruments such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite have greatly expanded these possibilities. Another method is the detection of gravitational waves. As discussed, gravitational waves can provide crucial information about events and processes that occurred during the formation of the universe, and possibly shed light on conditions preceding the Big Bang. Identification of gravitational waves caused by primordial waves, if it proves possible, will confirm specific models of inflation and pre-existing states. Theoretical work also plays an important role in verifying the conditions that preceded the Big Bang. Physicists are exploring concepts such as string theory, loop quantum gravity, and the equirodic model, which put forward different scenarios for the origin of the universe. These theoretical constructs can generate predictions that provide information about what can be detected in our modern universe. Comparing these predictions with observed phenomena allows scientists to assess the plausibility of different theories. In addition, laboratory experiments and high-energy particle physics using particle gas pedals such as the Large Hadron Collider allow us to investigate fundamental forces and interactions that were likely important in the earliest moments of the universe. By recreating similar conditions that existed shortly after the Big Bang, researchers can analyze the behavior and interactions of particles, which provides insight into the forces and elements that shape the universe. While testing theories concerning conditions that existed before the Big Bang is inherently difficult, the combination of observational astrophysics, gravitational wave research, theoretical modeling, and high-energy particle physics opens up various avenues to further our understanding. Through ongoing research and new discoveries, scientists are striving to build a holistic picture of the origin of the universe and the conditions that prevailed before the Big Bang. Particle gas pedals play a critical role in the study of physics before the Big Bang, allowing scientists to recreate and study extreme conditions like those believed to have existed in the early universe. These powerful machines accelerate charged particles to nearly the speed of light and collide them with each other, creating high-energy collisions that produce a variety of particles and phenomena. By studying these interactions, researchers can gain valuable insights into the fundamental forces and particles that governed the universe shortly after the Big Bang, and possibly in the moments before it. One of the key interests in pre-Big Bang physics is understanding the unification of fundamental forces. Particle gas pedals, such as the Large Hadron Collider, allow the exploration of energy levels that can shed light on how forces such as electromagnetism, strong nuclear forces and weak nuclear forces could have come together at higher energies. These experiments allow us to test theoretical models that predict the interaction of these forces under conditions similar to those of the early universe, and thus provide clues to unraveling the unification processes that may have occurred before the universe cooled and expanded. In addition, particle collisions can create conditions that mimic the high-energy environment thought to have been present during cosmic inflation, the rapid expansion immediately after the Big Bang. By studying the particles that formed and any potential signatures of the forces that emerged, researchers can gather evidence to support or refute various inflationary models. For example, they can detect hints of new particles or interactions that point to mechanisms that could cause inflation or support the idea of symmetry breaking when unified forces separate as the universe expands. In addition, particle gas pedal experiments can help scientists explore phenomena related to the state of the early universe, such as the formation of dark matter and dark energy. Understanding how particles behave under extreme conditions will help formulate hypotheses about the components that contributed to the evolution of the universe. High-energy collisions can also produce exotic states of matter, such as quark-gluon plasma, which can provide additional context for understanding transitions between different phases of matter in the early universe. Particle gas pedals are essential tools for studying conditions that existed before the Big Bang. By recreating a high-energy environment that reflects the formative moments of the universe, these facilities allow scientists to test fundamental theories, study the unification of forces, and explore the nature of the matter and energy that formed the universe. Through these efforts, researchers are gradually piecing together a more complete understanding of the origin of the cosmos and the mechanisms that govern its evolution. The anthropic principle raises intriguing questions when considering pre-Big Bang theories, primarily because it links fundamental properties of the universe to the existence of conscious observers like us. This principle exists in two main forms: the weak anthropic principle, which suggests that the observed values of the universe are due to the necessity for the existence of conscious beings, and the strong anthropic principle, which argues that the universe must have properties that allow for the emergence of life. When considering the anthropic principle in the context of pre-Big Bang theories, it is important to examine how initial conditions and physical constants affect the development of a universe capable of supporting life. Many pre-Big Bang theories, such as cosmic inflation or string theory, suggest the existence of a range of possible universes, each with different fundamental parameters. This leads to the concept of a multiverse in which our universe is just one of many, each with its own physical laws and conditions. Within this framework, the anthropic principle helps explain why we find ourselves in a universe that appears to be perfectly designed for life. We may just be living in one of the few universes within the multiverse that supports life. By applying the anthropic principle, researchers can explore how certain conditions that existed before the Big Bang could have led to the emergence of a universe with the properties necessary for life. For example, they can explore how certain asymmetries in the early universe or variations in fundamental constants can lead to the creation of a habitable environment. Such discussions can help refine pre-Big Bang theories by identifying measurable predictions that can be tested against observational data. However, the inclusion of the anthropic principle is also fraught with difficulties. Critics argue that it represents a form of circular reasoning, where the existence of observers is used to explain the structure of the universe. Thus, while the anthropic principle can guide theoretical reasoning, it must also be complemented by rigorous scientific research and empirical verification. This means that any pre-Big Bang theory inspired by the anthropic principle must be based on observable phenomena and rigorously tested. Ultimately, considering the anthropic principle in the context of pre-Big Bang theories contributes to a broader understanding of the origin of the universe. It encourages scientists to investigate how the initial conditions and potential scenarios of the multiverse may have affected the fundamental properties we observe, allowing researchers to seek deeper connections between cosmology, theoretical physics, and the existence of conscious life. Current technology has a number of limitations in exploring the earliest moments of the universe, especially those that occurred just after the Big Bang. One major problem is the impossibility of obtaining direct observational data on the very nascent universe itself, since it was obscured by a dense hot plasma that did not become transparent to radiation until 380,000 years after the Big Bang. Consequently, we are left to analyze circumstantial evidence, mainly through the cosmic microwave background radiation and the large-scale structure of the universe, which only give us a glimpse of the conditions of the early moments of the universe. Another limitation is the energetic scale required to recreate conditions similar to those in the early universe. The energies of particle interactions that characterize the moment after the Big Bang far exceed the capabilities of today's particle gas pedals. While facilities such as the Large Hadron Collider provide extensive data on high-energy processes, they cannot yet probe the extremely high-energy regimes associated with phenomena such as cosmic inflation or the unification of fundamental forces. In addition, our current observational instruments are limited in their ability to detect more subtle features associated with the early universe. For example, it is expected that primordial gravitational waves generated during inflation may carry crucial information about the formation of the universe. However, the sensitivity required to detect these waves is beyond the capabilities of our current telescopes and detectors, especially for very long wavelengths that indicate inflationary processes. Upcoming missions can work to improve this sensitivity, but until they are operational, our ability to study these early moments remains limited. In addition, theoretical frameworks continue to push the boundaries of our understanding of pre-Big Bang physics, but many of these theories lack definitive experimental confirmation. For example, concepts such as string theory or loop quantum gravity offer great insights into the nature of spacetime and the origin of the universe, but remain largely untested in laboratory and observational settings because of the energy scales and environments they propose. Connecting these theoretical ideas with empirical data remains a major challenge. Although technological advances have expanded our ability to study the origin of the universe, limitations in direct observations, energy scale capabilities, sensitivity to primordial signals, and empirical confirmation of theoretical models point to continuing challenges in studying the earliest moments of the universe. It is hoped that as research progresses and new technologies become available, these problems will be addressed, expanding our understanding of the fundamental beginnings of the cosmos. Dark matter plays a critical role in our understanding of the earliest states of the universe, allowing us to understand the structure and evolution of the cosmos shortly after the Big Bang. While dark matter itself remains elusive and has not yet been directly detected, its presence can be inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Understanding how dark matter interacts with the other components of the universe helps shed light on the conditions that prevailed during its formative moments. The earliest states of the universe, just after the Big Bang, rapid expansion and cooling processes produced primordial particles. These particles include ordinary matter, protons, neutrons, and electrons, as well as dark matter particles whose exact nature is still unknown, but are widely believed to be non-baryonic and fundamentally different from the matter that makes up stars, planets, and beings like us. The interaction of dark matter with ordinary matter probably played an important role in the formation of the initial density fluctuations that later evolved into galaxies and galaxy clusters. The significance of dark matter becomes particularly clear when studying the cosmic microwave background radiation. Fluctuations in this radiation provide a glimpse of the universe about 380,000 years after the Big Bang. Analysis of these fluctuations suggests that dark matter must have contributed to the gravitational wells that facilitated the cohesion of ordinary matter, leading to the formation of the first structures in the universe. This interaction between dark and ordinary matter has contributed to the evolution of the universe, influencing the patterns we observe today. Moreover, observations of large-scale structure show that dark matter drives the behavior of galaxies and galaxy clusters. The gravitational influence of dark matter helps explain the rotational velocities of galaxies that would otherwise not match the observed distribution of visible matter. This influence provides important clues about the distribution of matter in the early universe and helps to reconstruct the chronology of cosmic evolution. Dark matter is integral to our understanding of the earliest states of the universe, influencing the formation of structures, density fluctuations, and the overall dynamics of cosmic evolution. By studying how dark matter interacts with normal matter and affects large-scale structures, researchers can gain valuable insights into the processes that occurred shortly after the Big Bang and deepen our understanding of the fundamental forces that govern the cosmos. The distribution of galaxies provides important clues about the conditions that existed before the Big Bang and allows us to understand the processes that shaped the universe shortly after its formation. By analyzing the arrangement of galaxies in space, scientists can infer the underlying structure and dynamics that governed the early universe. This research is primarily concerned with the observation of the cosmic web, a vast network of galaxies, clusters, and filaments resulting from gravitational interactions driven by dark matter. One important aspect of the distribution of galaxies is that it reflects the initial density fluctuations that existed in the universe shortly after the Big Bang. When the universe became transparent to radiation about 380,000 years after the Big Bang, these fluctuations set the stage for gravitational collapse. Areas of slightly higher density attracted more matter, leading to the formation of galaxies and clusters. Thus, the cosmic structure observed today is a snapshot of the results of cosmic inflation and the subsequent evolution of these initial density fluctuations. In addition, the large-scale distribution of galaxies provides valuable information about the expansion of the universe. The correlation between galaxy clustering and redshift measurements allows cosmologists to reconstruct the history of cosmic expansion and the influence of dark energy over time. By tracing the position of galaxies, researchers can model how gravitational interaction shaped the large-scale structure of the observable universe, hinting at the laws of physics and conditions that existed in the early universe. In addition, studying the distribution of galaxies helps us understand the role of dark matter. Galaxies tend to form at the edges of dark matter halos. Halo interactions affect how galaxies cluster and distribute into larger structures. By mapping the distribution of galaxies, scientists gain insight into the underlying structure of dark matter, which has played a crucial role in the formation and evolution of cosmic structures, reflecting the dynamics present in the pre-Big Bang state. Overall, the distribution of galaxies provides a rich source of information about conditions that existed before the Big Bang. By simplifying complex cosmic structure and evolution into observable patterns, researchers can gain crucial clues about the initial conditions that formed the universe, as well as the fundamental laws that govern its evolution. The location of each galaxy is a piece of the puzzle, helping to reconstruct the history of the early universe and the processes that drove cosmic evolution. The apparent fine-tuning of universal constants is a fascinating topic that touches on the very nature of our universe. Before the Big Bang, the conditions and rules governing the universe as we know it did not yet exist. However, theories based on the assumption that the specific values of these constants, which seem to be carefully calibrated for the existence of galaxies, stars, and life itself, may be due to a variety of factors. One intriguing explanation is provided by string theory, which posits that the fundamental building blocks of the universe are not point particles but tiny vibrating strings. This theory proposes a scheme in which fundamental constants may arise from the shape and size of additional dimensions that we do not encounter in everyday life. These extra dimensions could lead to a variety of possible constants in different configurations, hinting at a landscape of universes, each with its own set of rules. Another assumption that existed before the Big Bang is the concept of a multiverse. According to this theory, our universe is just one of countless others, each with its own constants and laws of physics. In such a multiverse, fine-tuning may be the result of natural selection among these universes. Only those in which the right conditions for the formation of structures and the emergence of life have developed will be available to our observation, making our universe appear finely tuned, when in fact it may be just one of many. In addition, there are models based on quantum gravity that suggest that the universe may have undergone a transitional period before the Big Bang. According to this view, classical physics and its constants may have arisen from the more fundamental quantum realm. The variability of constants during transitions may explain the fine-tuning we observe today, shifting the focus from mere coincidence to a deeper basis of reality that has yet to be fully understood. This interplay between theoretical frameworks and emerging evidence invites ongoing exploration of the very fabric of our cosmos. The pre-Big Bang theories profoundly challenge our usual understanding of cause and effect, particularly because they propose a state of existence that lies outside of time and space as we know it. In our daily lives, we observe a clear and logical sequence of events. Causes lead to effects, forming a chain of action that makes sense. However, when considering the origin of the universe, especially before the Big Bang, our usual causal explanations become difficult to apply. One of the most compelling ideas preceding the Big Bang is the idea of a singularity, a point at which the laws of physics as we understand them break down. In this singularity, traditional notions of time and space would not exist, which means that the cause of the Big Bang could be radically different from anything we can observe. Without time, the concept of causality loses its usual meaning, complicating our ability to linearly trace the origin of the universe. Another intriguing aspect has to do with theories related to quantum mechanics. In the realm of quantum physics, particles can exist in states that do not conform to the classical rules of causation. Events can occur for no apparent reason, or even under the influence of factors that we cannot yet fully observe. Pre-Big Bang models that incorporate quantum fluctuations suggest that the very fabric of the universe itself could generate spontaneous events, such as the creation of matter, without the direct cause and effect relationships we take for granted in our macroscopic world. In addition, considering a multiverse scenario also complicates causality. If our universe is only one of many, then the events leading up to the Big Bang could have occurred in a completely separate context, further distancing the cause from the observed state. The multiverse suggests that universes may arise through quantum processes or mechanisms that do not obey the usual rules of causality. This profound shift in perspective forces us to rethink our fundamental assumptions about the nature of existence, ultimately broadening the horizons of our understanding of the cosmos. Models of an eternal universe offer a radical shift in our understanding of creation, challenging traditional views that have existed for centuries. In contrast to the idea that the universe had a definite beginning, such as the Big Bang, these models suggest that the universe has no starting point and instead exists in a perpetual cycle of creation and destruction. Such a viewpoint forces a reconsideration of the meaning of creation, because it implies that the universe is eternal and self-sufficient. One important consequence of eternal universe models is the notion that creation is not a single historical event, but a continuous process. For example, cyclic models assume that the universe goes through endless cycles of expansion and contraction, where each cycle leads to a new stage of existence. This concept suggests that instead of looking for a moment of origin, we should look at the universe as a continuously evolving system in which new entities and phenomena are constantly emerging. These models also raise philosophical and existential questions about purpose and meaning. If the universe is eternal and constantly renewing itself, how does this translate into ideas about human existence and the meaning of the creation of life? Belief in an eternal universe can support a more holistic understanding of existence that emphasizes interconnectedness and dynamism rather than a linear trajectory that begins and ends. This view may change spiritual and philosophical understandings of the universe, encouraging people to consider a deeper connection to the cosmos that has always existed in some form. In addition, theories of an eternal universe influence our scientific endeavors by encouraging researchers to study the various physical laws and properties that govern the infinitely existing universe. By studying the mechanisms underlying perpetual change, scientists may discover new insights into the nature of time, energy, and the ways in which cosmic structures evolve. The implications of these models thus extend far beyond cosmology, fostering a broader dialogue in which science, philosophy, and spirituality are intertwined as we attempt to understand our place in this potentially infinite universe. Theories before the Big Bang represent a fascinating intersection with various religious cosmologies, both aligning with and challenging traditional ideas about the origin of the universe. Many religious narratives contain creation stories that describe a specific moment of creation, often attributed to a divine being or force. In contrast, pre-Big Bang theories tend to assume the existence of the universe prior to a single starting point, advancing concepts such as eternal existence or cyclical creation, which can both complement and contradict these spiritual views. For example, some interpretations of ancient philosophies and religious traditions suggest that the universe is eternal, which echoes the ideas of Hindu cosmology, which describes an endless cycle of creation, conservation, and destruction. Cyclical models of the universe align well with these beliefs, suggesting that creation is not a one-time event, but a continuous process of rebirth and transformation. These similarities allow for a potential dialogue between the scientific narratives of pre-Big Bang theories and some spiritual interpretations, reinforcing the idea that the universe is a dynamic entity. On the other hand, many religious cosmologies, especially those influenced by Judeo-Christian narratives, emphasize a clear beginning defined by an act of divine creation. Concepts such as creatio ex nihilo, which translates to creation from nothing, position the universe as having a specific starting point, with creation having been masterfully designed and executed by divine power. Pre-Big Bang theories, which assume the existence of the universe in some form prior to our current conditions, may challenge these beliefs, raising questions about the nature of the role of the divine in creation and whether existence depends on an original cause. In addition, the implications of multiverse theories may diverge further from religious views. This concept suggests that there could be multiple universes with different laws and constants, complicating the idea of a single purposeful act of creation. Such ideas can prompt debate about the nature of divinity and the uniqueness of human existence. Exploring pre-Big Bang models forces a rethinking of traditional cosmologies and stimulates an ongoing conversation between science and faith, showing how our understanding of the universe continues to evolve and challenge long-held notions of creation. The possibility of a multiverse raises a myriad of profound philosophical questions that challenge our understanding of existence, reality, and our place in it. One central question concerns the nature of reality itself. If multiple universes coexist with different laws of physics, constants, and even different histories, what does this mean for our understanding of what reality is? The existence of parallel universes complicates our notion of uniqueness and uniqueness. It forces us to rethink the meaning of our experiences and choices in a potentially infinite array of alternatives. Another intriguing question concerns the nature of existence and the criteria for defining life and consciousness. If different physical laws and conditions can exist in multiple universes, how can we determine which reality is inhabited by intelligent beings? This leads to the philosophical question of whether life is a rare phenomenon limited to our universe, or whether it can exist in a myriad of realities. Such implications may alter our understanding of consciousness, prompting a debate about whether forms of experience in other universes might be radically different from our own. possibly challenging anthropocentric views of life. In addition, the concept of free will is called into question within the multiverse. If all possible outcomes exist in countless universes, does this diminish the significance of our choices? Are we merely participants in a complex web of outcomes that play out in different realities, making personal power seem insignificant? Alternatively, proponents of the multiverse theory may argue that the existence of multiple outcomes emphasizes the importance of every decision we make, since each choice can lead to new realities. Such discussions prompt a reassessment of moral responsibility and the importance of human decision-making. Finally, in the context of the multiverse, the questions of purpose and meaning take on new dimensions. If our universe is only one of many, and life emerges in various forms in different realities, what does this imply about humanity's role in the grand scheme of existence? Questions about purpose become complex and multifaceted. Like everyone else, people should consider whether meaning is set on a universal scale or emerges in each reality. This study not only challenges metaphysical beliefs, but also prompts a deeper examination of our motivations and values within the broader tapestry of existence. Theories prior to the Big Bang significantly affect our understanding of the purpose of the universe, offering a whole range of interpretations of existence itself. Traditionally, many philosophical and theological views have endowed the universe with a specific purpose, often based on the belief that it was created by a divine being with specific intentions. However, when considering pre-Big Bang models, which suggest that the universe may be eternal or exist in a state of perpetual change, the idea of purpose becomes more subtle and complex. One perspective emerging from pre-Big Bang theories is that the existence of the universe may not depend on a predetermined purpose or goal. Instead, the universe can be seen as a dynamic system governed by natural laws and processes, where existence itself is an ongoing event rather than a goal-oriented outcome. This perspective challenges anthropocentric beliefs that place human existence at the center of a grand cosmic plan. In this context, life and consciousness emerge as phenomena in an evolving cosmic structure rather than as endpoints of divine design. Moreover, cyclical models assume that the universe goes through endless cycles of expansion and contraction. This perspective presents existence as a series of rebirths, potentially leading to the conclusion that purpose is fluid and changeable rather than fixed. In such a scenario, each cycle opens up opportunities for different forms of structure, intelligence, and experience, further complicating the notion of a single overarching purpose. This evolving reality may invite people to create their own meanings in each cycle, fostering a more personal understanding of the purpose associated with human experience. On the other hand, some interpretations of pre-Big Bang theories may contribute to a renewed sense of wonder and exploration of the cosmos. The absence of a well-defined purpose does not mean a lack of significance. Rather, it opens up room for curiosity and discovery. People may find meaning in the pursuit of knowledge of the universe, in understanding its complexities, and in the relationships formed in the midst of expansive existence. A sense of autonomy and an understanding of one's role in the universe can be a powerful motivator, suggesting that humans are capable of infusing their lives with purpose even in a universe that may not adhere to a fixed teleological endpoint. Ultimately, theories that existed before the Big Bang challenge us to reflect on our understanding of existence, encouraging different interpretations of purpose that align with an ever-expanding view of the cosmos. The implications of pre-Big Bang theories for the concept of free will are profound and multifaceted, as they invite us to rethink the nature of choice, determinism, and the cosmos itself. At the heart of this discussion is the relationship between the origin of the universe and what abilities humans possess. If the universe functions according to laws that emerged under conditions prior to the Big Bang, the question arises whether our decisions are determined by these fundamental processes or whether true free will exists independently of them. One important consideration is the nature of causality itself. If pre-Big Bang models suggest that time and space as we understand them did not exist before the Big Bang, Then, the traditional chain of cause and effect becomes complex. This could mean that our decisions may be influenced by factors beyond our understanding, leading to a deterministic view where every action is the result of prior states. If free will is merely an illusion created by complex interactions within an overarching deterministic framework, this may challenge our understanding of personal responsibility and moral autonomy. Conversely, some interpretations of pre-Big Bang theories, particularly those that emphasize quantum mechanics, may provide the possibility for the existence of free will. In the quantum realm, events can be probabilistic rather than strictly certain. If the universe is fundamentally uncertain, this uncertainty may provide a basis for free will, allowing individuals to make choices that are not rigidly bound to pre-existing conditions. In this case, individual responsibility may emerge as a complex interplay of deterministic laws and random quantum events, allowing a sense of autonomy in decision-making. Moreover, if we consider cyclical models of the universe, in which the universe goes through repeated cycles of expansion and contraction, this may lead to a broadening of the range of possibilities for existence and choice. Each cycle may present a new set of circumstances and pathways that provide individuals with the opportunity to make different decisions. In this light, free will may manifest itself as the ability to make choices within a dynamic framework, meaning that despite the constraints imposed by the structure of the universe, the potential for different experiences and decision-making ultimately exists. Ultimately, the interplay between pre-Big Bang theories and the concept of free will prompts an exploration of the complexities of human experience. Reflecting on the nature of individuality in a potentially entangled and multi-layered universe, we are prompted to consider the balance between determinism and freedom, inviting philosophical reflection on the responsibility and possibilities that are associated with our choices in a vast and mysterious cosmos. Pre-Big Bang models have a profound impact on our view of the uniqueness of our universe, challenging the idea that our cosmos is a single, exclusive creation. One important consequence of these models is the conceptualization of the multiverse, which assumes the existence of multiple universes, each with its own physical laws, constants, and characteristics. This notion directly questions the singularity of our universe, suggesting that what we perceive as unique may be just one manifestation in a vast tapestry of realities. When considering cyclical models which assume that the universe goes through endless cycles of expansion and contraction, the implications of uniqueness become even more profound. If our universe is just one in a series of rebirths, then the attributes we often consider special can be replicated or transformed in countless subsequent iterations. This viewpoint is forcing us to reconsider our perception of significant cosmic events, including the formation of stars, galaxies, and even life. Rather than viewing the characteristics of our universe as rare, cyclic models invite us to think of them as part of a larger, ongoing cosmic process. Moreover, the quantitative nature of the eternal universe scenarios further enriches this dialogue about uniqueness. If the universe has an infinite timeline in which all possible scenarios can occur, then the unique circumstances of our existence may be just one of many potential realities. This expansive view can diminish the sense of individual significance often attributed to our cosmos. It emphasizes the idea that there may be many similar or even completely different instances of existence elsewhere, now or in the infinite future. However, this does not mean that the universe is devoid of significance or beauty. Recognizing multiple universes or cycles can also increase appreciation of our existence in a surprising and possibly random context. Realizing that our universe may share commonalities with many others can generate a sense of wonder and curiosity about what we can learn from it. Ultimately, while pre-Big Bang models challenge our perception of uniqueness, they also promote a deeper exploration of existence by inviting us to appreciate our universe within a larger, intricate cosmic narrative. The various models of the origin of the universe present compelling ethical considerations that make us think about our responsibilities, relationships, and understanding of existence. One notable consideration has to do with the deterministic implications of some models, such as those that assume that conditions preceding the Big Bang lead to the inevitable unfolding of events. Assuming that our decisions are determined by physical laws or the circumstances of the universe's creation challenges the concept of moral responsibility. Are humans responsible for their actions if every choice they make can be traced back to predetermined cosmic events? This question provokes vital discussions about justice and responsibility in a potentially deterministic world. Conversely, models that emphasize randomness and uncertainty, such as quantum mechanics, open a framework for personal agency and ethical behavior. If choices can emerge from uncertain conditions, then people may have a greater sense of autonomy in shaping their destiny. The inherent freedom we have may raise the ethical stakes involved in decision-making, prompting greater reflection on the impact these decisions have on ourselves and others. Recognizing that people can influence the unfolding of events imposes a collective responsibility to act ethically and thoughtfully in the face of countless possibilities. In addition, theories of multiverses raise ethical questions about the nature of existence and the value of life. If there are multiple universes, each with different life forms, this may affect how we view our own existence and the consequences of actions taken in our universe. Are we morally obligated to care about the welfare of sentient beings in other potential universes? While direct interaction may not be possible, this idea encourages us to think beyond anthropocentric perspectives, fostering a broader sense of ethical duty toward any sentient beings that may exist in different contexts. Finally, the study of models of the universe raises broader ethical questions related to scientific research and technological advancement. As our understanding of the cosmos deepens, ethical considerations regarding the use of this knowledge become paramount. Should we responsibly consider developing new technologies based on these theories, given the potential consequences they may have on our own and other universes? The pursuit of knowledge of the universe must be accompanied by a commitment to ethical standards that prioritize the well-being of our planet, future generations, and unknown living beings that may exist elsewhere. Ultimately, these ethical considerations force us to consider how our understanding of the universe shapes not only our worldview, but also our moral framework as we make difficult choices in a confusing and ever-expanding cosmos. Exploring theories from before the Big Bang has significant implications for our understanding of consciousness and its relationship to the cosmos, inviting us to reconsider the nature of awareness in a broader cosmological context. One major implication is how these theories challenge the traditional view of consciousness as a unique characteristic of humans or life within a singular universe. If models such as the multiverse suggest infinite variations in physical laws and conditions, then the possibility of different forms of consciousness emerging in these different realities becomes an intriguing consideration. This expands the scope of the conversation about what consciousness is and how it may manifest in forms we cannot yet comprehend. Moreover, if pre-Big Bang scenarios indicate that our universe is just one iteration of many in an eternal or cyclical process, this raises questions about continuity and the evolution of consciousness. Cyclic models suggest that consciousness can arise repeatedly in different forms with each cycle. This conception suggests that consciousness is part of a larger process of existence, subject to the same dynamics that govern the universe, growth, decay, and rebirth. It raises the question of whether consciousness is transient or whether it is carried through various incarnations within the cycles of existence. This perspective can lead to a more interconnected view of the self, advancing the idea that consciousness is not isolated, but is part of a continuous cosmic interaction. In addition, the inclusion of quantum mechanics in the theories preceding the Big Bang introduces the idea of consciousness as an active participant in the unfolding reality. Some interpretations of quantum theory suggest that observation plays a crucial role in determining the state of a system. If consciousness influences particle behavior at a fundamental level, this may indicate that consciousness is not simply a byproduct of biological processes, but is woven into the very fabric of the universe. Such an understanding encourages a deeper exploration of the relationship between consciousness and physical reality, positioning awareness as a vital component in the ongoing story of the cosmos. Ultimately, the pre-Big Bang theories force us to consider the nature of consciousness as dynamic and inherently connected to the universe. By viewing consciousness through this expanded lens, we can appreciate it as a component of a larger cosmic narrative, which raises questions about the purpose, evolution, and potential of consciousness in different universes and experiences. This research enriches our understanding of mind and existence, emphasizing the potential for greater wisdom and interconnectedness with the cosmos. The implications of pre-Big Bang theories for the long-term fate of the universe are both intriguing and complex, and they shape our understanding of the ultimate fate of cosmic structures and the very fabric of existence. Different models propose multiple scenarios for the evolution of the universe, each with different implications for its future. For example, cyclic models suggest that the universe goes through endless cycles of expansion and contraction. Within this framework, each cycle ends with a cosmic upheaval leading to a new beginning. It suggests that rather than facing a definitive end, the universe may perpetually reinvent itself, fostering a sense of continuity and renewal. In contrast, theories assuming an eternal universe raise questions about the implications of an infinite time frame. If the universe is eternal, then it can go through different phases of evolution over unimaginable lengths of time. This scenario allows for a continuous transformation in which different structures and forms of matter can arise, decay, and evolve far into the future. The focus on the eternal universe prompts reflection on the nature of entropy, suggesting that while structures may decay over time, new configurations may emerge from the same fundamental building blocks, hinting at an ever-evolving cosmic landscape. In addition, pre-Big Bang models influenced by thermodynamics suggest the possibility of a universe that may eventually face a heat death, where all energy is uniformly distributed and thermodynamic processes cannot occur. In this scenario, the universe reaches a state of maximum entropy, resulting in a cold, dark space devoid of stars and active processes. This concept presents a rather bleak ending, emphasizing the inevitability of movement toward equilibrium and disorder. It challenges our understanding of the viability of the cosmos, forcing us to consider what sustainable existence means in the face of long-term entropy outcomes. In addition, the study of cosmological constants and their role in the fate of the universe, whether expanding or contracting, emphasizes the uncertainty of the final results. As researchers study these dynamics, understanding dark energy, dark matter, and their impact on cosmic evolution becomes crucial. The interaction of these forces can lead to different paths, whether it's a big crunch when the universe collapses or a big freeze when expansion continues indefinitely. In each case, pre-Big Bang theories significantly influence our conception of the future of the universe, forcing us to consider the nature of existence, the flow of time, and our place in the ongoing cosmic story, regardless of how it unfolds.